Welcome to the Late Lab. It's good to have you here. Before tonight's quiet journey begins, perhaps take a moment to notice where you are. Maybe you're settled beneath soft blankets, listening from a dim room while the rest of the house grows still. Maybe you're on a late bus, a slow train, or curled up somewhere with a drink slowly losing its warmth beside you. Wherever this finds you, hopefully the world feels a little softer now, and there is room to let the mind wander. If these gentle scientific wanderings help you relax, drift, or simply think about strange things in a calmer way, a like and subscribe helps this little corner of the internet keep glowing. And if you're already subscribed, thank you, sincerely. Your support gives these late-night experiments somewhere to land. Now, tonight's subject is a little dangerous in the most peaceful possible way, because it begins with nothing, and nothing, as it turns out, has a habit of becoming suspiciously interesting once science gets involved. So with any luck, this will be soothing enough to help you rest. But if it keeps one eye slightly open, at least you'll know a little more about why empty space may not be empty, why the vacuum can have energy, and why the universe seems rather reluctant to provide a clean blank page. A very gentle inconvenience, really. So let's begin, shall we? What is nothingness? And why does modern physics seem unable to leave it alone? Nothing sounds like it should be the simplest idea in the world. Take everything away, clear the room, empty the cup, let the light fade, let the noise settle, and there it is. Nothing. A neat little word for absence, a quiet word, a word that seems as if it should not cause much trouble. But in science, nothing is surprisingly difficult to pin down. The closer it is examined, the less empty it becomes. Empty space, which once seemed like a silent background where matter simply moved around, has become one of the strangest subjects in modern physics. It is not just a blank stage. It may have structure, energy, geometry, fields, and effects that can be measured. In other words, the universe seems to have taken the idea of nothing and quietly filled it with complications. This begins with a simple problem. In everyday life, nothing usually means that something expected is missing. There is nothing in the cupboard, meaning no food, no biscuits, and no emergency chocolate hiding heroically behind the pasta. There is nothing in the cup, meaning no tea, no coffee, and no mysterious cold liquid that everyone is politely pretending not to notice. There is nothing to hear, meaning a room is quiet enough that the faint hum of the house suddenly becomes obvious. But this everyday nothing is not true nothingness. An empty cupboard still contains air. An empty cup still contains molecules, warmth, and space. A silent room still contains pressure waves too faint to notice, surfaces holding heat, dust drifting slowly, and gravity pulling gently on everything inside it. Darkness is not pure non-existence either. It is simply the absence of enough visible light reaching the eye. Even silence and darkness, the two great ambassadors of nothing, turn out to be conditions within the world, not escapes from it. There is also philosophical nothingness, which is far more severe. This is not an empty room or a quiet sky. It is the complete absence of everything. No matter, no energy, no space, no time, no fields, no laws, no possibility, and no observer wondering where everything has gone. It is a difficult idea, because the moment the mind tries to imagine it, something usually sneaks in. A black void appears, a blank space appears, a kind of endless darkness appears. But darkness is still something. A void still has size. A blank space still feels like a place. True philosophical nothingness would not even be a lonely empty stage. It would be the absence of the stage itself. Physics usually cannot work with that kind of nothing. Science studies things that can be described, compared, measured, predicted, or detected through their effects. Absolute non-existence has no properties. It has no temperature, no size, no location, no duration, and no behavior. It offers no handle for an experiment to grasp. So when physics talks about emptiness, it is usually talking about physical emptiness, which is much more practical and much less absolute. A physical vacuum is a region where ordinary matter has been removed as much as possible. It can be studied in laboratories. It can be made cleaner or less clean. It can have pressure, temperature, boundaries, radiation, and fields. A vacuum chamber may remove almost all the air from a space, but it does not remove reality. A few particles remain. The walls of the chamber can release molecules. Light can pass through it. Gravity still acts. Electromagnetic fields may still be present. The chamber still occupies space-time. So a vacuum is not a hole where existence has failed. It is a physical state where much of the familiar material has been taken away. An empty room, then, is empty only in a casual human sense. A vacuum chamber is much emptier, but still not nothing. The space between galaxies is emptier still, yet even that is not true nothingness. Intergalactic space may contain stray particles, faint radiation, magnetic fields, ghostly neutrinos, and the ancient microwave afterglow left from the early universe. Matter there is spread unbelievably thinly, but thin is not the same as absent. Even the most deserted cosmic regions are not perfect blanks. They are more like vast, quiet places where reality has turned the volume almost all the way down, but not quite off. The space between atoms adds another twist. Ordinary solid objects feel continuous because human senses are not built to notice their inner gaps. A table feels solid. A stone feels solid. A hand resting on wood does not feel as if it is touching a cloud of mostly empty atomic structure. Yet atoms are made of tiny nuclei surrounded by electron clouds, and most of an atom's volume is not filled by solid stuff in the everyday sense. Still, that inner emptiness is not simple nothing either. It is shaped by electromagnetic forces, quantum behavior, and the rules that allow atoms and molecules to hold together. If empty space were truly just empty, matter would not have the structure it does. This is where modern physics begins to make nothingness feel deeply strange. In older thinking, space could seem like a passive container, the quiet background in which objects move. But Albert Einstein's general theory of relativity changed that picture. Space and time became spacetime, and spacetime could curve in response to mass and energy. Gravity was no longer simply a force travelling through emptiness. It became connected to the shape of space-time itself. That means even a region empty of ordinary matter can still have geometry. It can still be part of the physical structure of the universe. Quantum physics goes further. In quantum field theory, particles are understood as excitations of underlying fields. The electron is linked to the electron field. Light is linked to the electromagnetic field. Other particles are linked to their own fields as well. These fields are not sprinkled into space like furniture in a room. They are part of the basic description of nature. In this view, a vacuum is not the absence of fields. It is the lowest energy state of those fields. That may be the most important shift of all. Empty space is not necessarily empty of physical reality. It may be the quietest possible state of something that still exists. Then there is dark energy, the name given to the unknown cause of the accelerating expansion of the universe. Its true nature remains uncertain, but one possibility is that it is connected to energy associated with space itself. If that is correct, then the emptiest regions of the cosmos are not merely empty backgrounds. They may help shape the future expansion of the universe. So the science of nothingness begins with a word that seems simple and ends with one of the deepest puzzles in physics. Everyday nothingness is absence in a practical sense. Philosophical nothingness is the complete absence of all reality. Physical emptiness is something science can study, but every version of it seems to contain structure, fields, laws, or measurable effects. Nothing, it turns out, is not a blank answer. It is a question that refuses to stay empty. Long before anyone could build a vacuum chamber, seal a glass tube, or measure air pressure with a column of mercury, the idea of emptiness was already troubling the human mind. It was not only a question about space, it was a question about reality itself. Could there be a place where nothing existed? Could absence have a kind of presence? Could motion happen if there were no empty room for things to move through? These questions sound peaceful from a distance, almost like the kind of thing a person might wonder while staring into a dark sky. But for ancient thinkers, they were not gentle decorations. They were serious problems. Nothingness seemed difficult even to imagine. The mind tries to picture it and immediately gives it a shape. A dark cavern, a blank sky, a silent hollow. Yet each of those images is still something. Darkness is still an experience. A hollow still has edges. A blank sky still stretches across space. True nothingness refuses to behave like an ordinary object of thought. It does not sit still for the imagination. In the ancient world, this made the void both fascinating and suspicious. Many early thinkers tried to explain the world by asking what everything was made of. Some thought the basic substance was water. Others imagined air, fire, earth, or some more mysterious underlying material. These ideas may sound simple now, but they were part of a powerful shift. Nature was being treated as something that could be explained by principles rather than only by myth or divine mood swings, which, to be fair, would have made weather forecasting even more stressful than it already is. Among the boldest of these ancient ideas was atomism. The Greek thinkers Leucippus and Democritus argued that reality was made of tiny indivisible units called atoms, moving through empty space. The word atom comes from the Greek idea of something that cannot be cut. Their atoms were not atoms in the modern scientific sense, with nuclei, electrons, and quantum fields. They were imagined as eternal, solid, tiny pieces of matter, differing in shape and arrangement. Everything in the world, from stones to bodies to clouds, could be understood as combinations of these small units. But atomism required something just as important as atoms. It required void. Without empty space, the atoms could not move. They could not rearrange. They could not combine or separate. The void was not merely a useless absence. It had a role. It allowed change to happen. In that view, emptiness was not a mistake in reality. It was one of the conditions that made reality possible. Matter needed room, and the void provided it. This was a remarkable step. Leucippus and Democritus were not using telescopes, microscopes, or particle detectors. They were reasoning from change, motion, and the variety of the world. If things can move, there must be somewhere for them to move into. If objects can be divided, rearranged, and transformed, perhaps reality is built from smaller parts shifting through empty space. It was a vision of nature as restless, granular, and deeply structured, with the void woven into its explanation. Not everyone found this convincing. Aristotle, one of the most influential philosophers in history, rejected the idea of a true vacuum. He believed that empty space could not exist. In his view, nature was continuous, and places were always filled by something. The phrase often associated with this idea is that nature abhors a vacuum. The exact wording came later, but it captures the spirit of the argument well. For Aristotle, a void was not just unlikely. It seemed physically impossible. Aristotle had reasons for this. He thought about motion in a very different way from later physics. In his system, objects moved according to their nature and according to the medium around them. A stone fell through air or water. Fire rose. The heavens moved in their own special way. If there were a completely empty void, Aristotle argued, motion would become absurd. There would be no medium to resist movement, no meaningful distinction between places, and no natural way to explain why objects behaved as they did. To him, the vacuum was not a useful scientific idea. It was a threat to a coherent picture of nature. This disagreement between atomists and Aristotle mattered for far more than ancient philosophy. It created a question that would echo for centuries. Is emptiness a real part of the world, or only a mistaken idea produced by the mind? Is space a container that can exist without matter, or must every place be filled by something? Can nothing have a physical role? For a very long time, Aristotle's view carried enormous authority. His ideas shaped natural philosophy through the ancient world, the Islamic Golden Age, and medieval Europe, often being debated, refined, and combined with other traditions. This does not mean everyone simply agreed without thinking. Scholars such as John Philoponus challenged parts of Aristotelian physics, and later medieval thinkers examined the possibility of vacuum in careful ways. Still, the idea that nature resisted emptiness remained powerful. Part of the difficulty was that ancient thinkers could not easily test the question. They could argue about the void, but they could not yet make a controlled vacuum in the modern sense. They could watch air fill a space, water flow into a gap, or smoke spread through a room. They could see that nature often seemed to rush in where space had opened. But they did not have the instruments needed to remove air from a sealed region and ask what remained. That is what makes the ancient void so important. It shows that the science of nothingness began as a problem of thought before it became a problem of experiment. The early debate was not silly or primitive. It was aimed at a real difficulty. Motion seems to require openness. Matter seems to occupy space. Absence seems impossible to grasp. Even now, modern physics still circles a more precise version of the same question. Is empty space truly empty, or does it have properties of its own? The answer today is very different from anything Leucippus, Democritus, or Aristotle could have known. Modern physics has atoms, quantum fields, relativity, vacuum energy, and cosmic expansion. Yet the old question remains recognizable. The atomists suspected that emptiness allowed matter to move. Aristotle suspected that nature could not tolerate a true void. Both were reaching, in different ways, toward the problem that still sits beneath the word nothing. Eventually, this question would leave the open air of philosophy and enter the laboratory. The void would no longer be only something imagined in argument. It would be pursued through glass tubes, mercury columns, sealed vessels, pumps, and pressure. What had once been debated as an unsettling absence would become something that could be made, measured, and watched. And that quiet shift from imagined void to experimental vacuum would change the meaning of nothing forever. For centuries, the void had lived mostly in argument. It had been imagined, rejected, defended, and worried over by philosophers trying to decide whether empty space could exist at all. But eventually the question moved from the mind into the laboratory, though the laboratory in this case involved glass tubes, heavy liquid metal, careful hands, and the slightly alarming willingness to turn things upside down and see what happened. The old question was simple to ask and difficult to test. Could a space remain empty, even briefly, or would nature always rush in to fill it? For a long time, the answer seemed obvious from everyday experience. Pull water up through a pump and water follows. Open a gap and air enters. Try to create emptiness and the world appears to push back. It was easy to think that nature truly did abhor a vacuum, as if the universe had a deep personal dislike of blank spaces and was prepared to be quite dramatic about it. Then, in 1643, the Italian scientist Evangelista Torricelli carried out an experiment that changed the conversation. Torricelli had worked with ideas connected to Galileo Galilei, and he was interested in the behaviour of fluids, pressure, and the limits of suction pumps. At the time, miners and engineers knew that ordinary pumps could only raise water to a certain height. This was not just an annoying plumbing problem, it was a clue. Something about air, weight, and pressure was waiting to be understood. Torricelli used mercury, a dense silvery liquid metal instead of water. Mercury is much heavier than water, so a much shorter column could balance the pressure of the surrounding air. He filled a long glass tube with mercury, sealed one end, and turned it upside down into a basin also filled with mercury. Some of the mercury flowed down out of the tube, but not all of it. A column remained suspended, and above that column there appeared a small empty region. This empty region became known as the Torricellian vacuum. It was not absolute nothingness, and Torricelli didn't claim to have created a perfect philosophical void. But it was a sustained, empty-looking space inside the top of a sealed glass tube, where ordinary air had not simply rushed in. That mattered enormously. It suggested that the space above the mercury was not being held open by horror of a vacuum, or by some mysterious need for nature to avoid emptiness. Instead, the mercury column was being supported by the pressure of the atmosphere pressing down on the mercury in the basin. In other words, air had weight. That may sound obvious now, because modern life is full of weather reports, tyre pressure, air pressure, cabin pressure, and other reminders that air is not just a polite invisible nothing. But at the time, this was a powerful shift. Air was no longer just the transparent background through which people walked and birds flew. It was a physical substance. It pressed. It weighed. It could support a column of mercury. The atmosphere was not empty space around the world. It was a vast ocean of gas, and everyone lived at the bottom of it, generally without noticing, which is probably for the best. Torricelli's experiment gave nothingness a new scientific shape. The vacuum was no longer only a philosophical idea. It could be produced in a tube, watched, repeated, and measured. The height of the mercury column became a way to measure atmospheric pressure, which is the basic principle behind the mercury barometer. The empty space above it was not a perfect absence, but it was empty enough to challenge centuries of thinking. Blaise Pascal took the idea further. Pascal understood that if the mercury column was supported by the weight of the atmosphere, then the height of that column should change with altitude. Higher up a mountain, there is less air above, and therefore less atmospheric pressure. In 1648, Pascal arranged for measurements to be taken on the Puy de Dôme, a mountain in France. The mercury column stood lower at higher elevations, just as the pressure idea predicted. This was a beautiful moment in experimental science. A philosophical question had become something that could be tested by climbing a mountain with equipment, which is admirable, even if it does make modern complaints about carrying a laptop upstairs seem slightly less heroic. Pascal's work showed that pressure was not fixed by some mysterious tendency of nature, but changed depending on the amount of atmosphere above. The air had weight, and that weight could be measured. Around the same period, the German scientist and engineer Otto von Guericke built one of the first effective vacuum pumps. Instead of relying only on mercury in a tube, von Guericke could remove air from sealed containers. This allowed him to demonstrate the force of atmospheric pressure in a more dramatic way. His most famous demonstration involved the Magdeburg hemispheres, two metal hemispheres fitted together to form a hollow sphere. When the air inside was pumped out, the pressure of the outside atmosphere held the hemispheres tightly together. The effect was astonishing. Teams of horses were used in demonstrations to try to pull the hemispheres apart. The point was not that the hemispheres were magically stuck, but that the air outside was pressing on them with enormous force. Remove the air from inside and the balancing pressure was gone. The atmosphere did the rest. It was not a gentle suggestion from the sky. It was a physical push from the ocean of air surrounding the world. These early experiments did not create true nothingness. There were still traces of gas, vapour, radiation, and the material boundaries of the container. The glass tube, the mercury, the metal hemispheres, and the surrounding air all mattered. This new nothing had walls. It had pressure differences. It depended on materials, measurements, and careful preparation. It was not the absence of reality. It was a physical condition produced by removing some matter from a defined space. And that was the real breakthrough. The first scientific vacuum showed that absence could have measurable consequences. Removing air from a space changed what happened there. It allowed mercury to reveal atmospheric pressure. It allowed metal hemispheres to cling together under the weight of the surrounding air. It showed that what seemed like empty background was actually part of the physical system. The old idea of nature abhorring a vacuum began to give way to something clearer and more useful. Nature did not need to hate emptiness. Air pressure could explain what was happening. A vacuum was not impossible. It was simply difficult to make, never perfect, and never quite the same as true nothing. The first scientific nothing was not nothing at all. It was a carefully prepared space surrounded by matter, shaped by pressure, and full of meaning. Once the vacuum had been pulled out of philosophy and placed inside glass tubes, mercury columns and metal spheres, it became harder to dismiss. Empty space was no longer just an uncomfortable idea. It was something that could be prepared, observed, and measured. It still was not absolute nothingness, but it was real enough to make instruments respond. Classical physics gradually learned to live with a vacuum. Instead of treating it as a forbidden impossibility, scientists began to understand it as a region with little or no ordinary matter. A vacuum could be imperfect, partial, and practical. It could be made in a vessel or imagined in the space between worlds. The important change was subtle, but enormous. Empty space was no longer assumed to be a contradiction. It became part of the physical picture. This mattered because the universe was getting larger in human thought. The Earth was no longer seen as the still centre of everything. Planets moved around the sun. Comets swept through the sky on long returning paths. Moons circled planets. Astronomers were beginning to imagine the heavens not as a set of perfect crystal spheres, but as a vast region where bodies move through space according to regular laws. And for that to make sense, space had to be more than a local gap between objects. It had to be the arena in which motion happened. Isaac Newton gave this picture its most powerful classical form. In his great work, Mathematical Principles of Natural Philosophy, published in 1687, Newton described laws of motion and universal gravitation that could apply to falling apples, orbiting moons, planets, and comets alike. The same mathematical rules could connect a stone dropping near Earth with the moon circling overhead. The universe became more unified and also more spacious. In Newton's view, space was often treated as absolute. It existed as a kind of fixed stage, a background against which motion could be measured. Matter moved through it. Forces acted within it. Events happened in it. But space itself was not usually imagined as a substance with moods, texture, or inactivity. It was more like the quiet theatre in which nature performed. A very large theatre, admittedly, and one with no obvious snack interval. This made emptiness seem less threatening. If space was an absolute stage, then a region without matter could still be a real region. Empty space did not have to collapse into contradiction. It could simply be space with no bodies inside it. A planet could travel through a vast near vacuum without needing air to carry it. A comet could sweep through the solar system without being pushed along by some hidden wind. Motion did not require a thick material medium in the old everyday sense. Newtonian mechanics helped clarify this beautifully. An object in motion did not need continuous pushing to keep moving. According to Newton's first law of motion, a body remains at rest or continues moving uniformly unless acted on by a force. This idea changed the older intuition that motion always needed something to sustain it. In empty space with little resistance, a body could continue moving simply because nothing was there to slow it down. Emptiness became useful. It allowed motion to be clean, persistent, and mathematically understandable. This was very different from ordinary life, where objects quickly stop because friction, air resistance, and contact forces drain motion away. A cup sliding across a table slows because the table and air interfere. A thrown ball falls because gravity acts on it, and air resists it. But in the nearly empty regions between planets, those everyday interruptions become much smaller. The vacuum was not a problem for motion. In many ways, it revealed motion more clearly. Classical thinking separated several ideas that had often been tangled together. Matter was the stuff of bodies, planets, stones, air, water, and all the ordinary materials of the world. Space was where those bodies were located and through which they moved. Force was what changed their motion. Gravity was one such force, and Newton's law of universal gravitation said that every mass attracts every other mass. Earth pulls on the moon pulls on Earth, the sun pulls on the planets. Every object with mass participates in this quiet, mutual tug. Here, though, the old mystery of nothingness returned in a new form. Gravity appeared to act across empty space. The sun could influence Earth without a visible rope, rod, wind, or stream of matter connecting them. The moon could raise tides across a distance. Planets could curve their paths in response to the sun's attraction, even though most of the space between them seemed empty. Newton understood that this was strange. His theory described gravity's effects with extraordinary success, but the deeper mechanism remained unclear. How could one body influence another across a void? How could a force reach through nothing? This became known as the problem of action at a distance. The mathematics worked brilliantly, but the physical picture felt incomplete. Empty space had become acceptable, but it had not become entirely comfortable. Newton himself was cautious about pretending to know more than he did. He could describe how gravity behaved, but he didn't claim to explain its ultimate cause. That restraint is one of the quieter strengths of science. Sometimes a theory can be incredibly accurate while still leaving a deeper question glowing gently in the background, like a candle someone forgot to blow out before bedtime. So the classical vacuum was not the absolute nothing of philosophy. It was not the quantum vacuum of modern physics either. It was a region with little or no matter, a passive stage where bodies could move and forces could be described. Yet even in this calmer picture, emptiness carried a puzzle. Space could be empty of ordinary stuff, but gravity still seemed able to cross it. That tension would not disappear. It would wait patiently inside the idea of the vacuum, until later physics began to ask whether empty space was truly passive at all. The classical vacuum made empty space seem possible, but it did not make it completely peaceful. Matter could move through emptiness. Gravity could act across it. Planets and comets could travel through vast regions with almost no air at all. Yet one major question still lingered, soft but persistent. What about light? Light behaved like a wave. It could reflect, refract, interfere, and spread in ways that look beautifully wave-like. But in ordinary experience, waves usually need something to wave. Sound travels through air, water, wood, or metal. Ocean waves travel through water. Ripples move across the surface of a pond. If light was a wave, then it seemed natural to ask what carried it across the emptiness between the sun and earth. The answer many scientists accepted was the luminiferous ether. The word luminiferous meant light-bearing, and the ether was imagined as a subtle medium filling all of space. It had to be strange stuff. It needed to be thin enough that planets could move through it without being slowed down, but firm enough to carry light waves at enormous speed. It had to fill the heavens, pass through ordinary matter, and somehow remain almost perfectly invisible. In other words, it was expected to do quite a lot while leaving no forwarding address. The ether was not a foolish idea at the time. It was an attempt to make sense of light using the best wave concepts available. If waves needed a medium, and light was a wave, then perhaps space was not truly empty after all. Perhaps it was filled with a hidden substance too delicate for the senses but essential for physics. Then came James Clerk Maxwell. In the 19th century, Maxwell brought together electricity, magnetism and light in one of the great achievements of science. His electromagnetic theory showed that changing electric fields and changing magnetic fields could sustain one another and travel as waves. The speed predicted by his theory matched the known speed of light closely enough to reveal something profound. Light itself was an electromagnetic wave. This was a beautiful unification. Electricity, magnetism, and optics were not separate kingdoms. They were connected parts of one deeper pattern. But Maxwell's work also sharpened the old puzzle. If light was a wave of electric and magnetic fields, what were those fields waving through? Many physicists still assume the answer was ether. The electromagnetic fields seem to be a disturbance in some underlying medium, much as sound is a disturbance in air. The trouble was that if Earth moved through this ether as it orbited the Sun, then that motion should be detectable. It would be a little like moving through still air. When travelling forward, there is a breeze against the face. If Earth travelled through ether, perhaps light moving in different directions would behave slightly differently depending on the planet's motion through that invisible medium. In 1887, Albert Michelson and Edward Morley carried out a famous experiment to look for exactly this effect. Their device, known as an interferometer, split a beam of light into two paths at right angles, sent the beams out and back, then recombined them. If Earth were moving through ether, light travelling along one path should take a slightly different time from light travelling along the other. That difference should show up as a shift in the interference pattern. The experiment was carefully designed and remarkably sensitive for its time. It was looking for the so-called ether wind, the sign of Earth pushing through the light-bearing medium. But the expected effect didn't appear. The result was essentially null. Earth's motion through the supposed ether could not be detected in the way the theory predicted. This did not instantly destroy the ether in one dramatic puff of 19th century embarrassment. Science rarely works that neatly. Some physicists tried to rescue the idea with additional explanations, including the possibility that objects contracted slightly in the direction of motion through the ether. Hendrik Lorentz and George Fitzgerald developed ideas along these lines, and their work later became historically important in the path toward relativity. But the absence of a detected ether wind became a turning point. It suggested that the old mechanical picture of light moving through a hidden substance might be wrong. Empty space might not need to be filled with an ordinary medium for light to travel. The vacuum did not have to behave like invisible jelly, which is probably a relief to everyone involved. Albert Einstein's special theory of relativity, published in 1905, changed the picture more deeply. Light didn't need a mechanical ether in the old sense. The speed of light in vacuum became a fundamental feature of nature, the same for all observers moving at constant speed. Space and time themselves had to adjust around that fact. The strange medium once invented to support light was no longer necessary. This was not merely the failure of a bad idea. It was a profound step in understanding space, light, and motion. Removing the ether cleared the way for a new kind of emptiness. The vacuum could carry electromagnetic waves, not because it was filled with a familiar material substance, but because electric and magnetic fields are part of the physical structure described by the laws of electromagnetism. They are not ripples in air, water, or a hidden cosmic fluid. They are fields, and fields do not need to be made from tiny gears and springs to be real. Still, the ghost of the ether is worth treating gently. It reminds us that scientists were trying to answer a reasonable question. If light is wave-like, what supports the wave? The answer changed as physics changed. The failure to find ether did not make space simple. It made space stranger. Later, quantum field theory would describe empty space as filled with fields in a very different sense. This should not be confused with bringing the old ether back. Quantum fields are not a mechanical substance through which Earth drifts, and they do not define a single preferred state of absolute rest. They belong to a more modern and more precise framework. Even so, both ideas reveal the same quiet discomfort. Empty space keeps refusing to be merely empty. The ether vanished, but the question it tried to answer did not. Light crossed the vacuum, fields remained real, and nothingness once again turned out to be less blank than it first appeared. The disappearance of the ether did not leave physics with a simple empty stage. It left something stranger. Light no longer needed a hidden mechanical substance to carry it through space, but that raised an even deeper question. If the vacuum was not filled with ether, then what exactly was space? Albert Einstein changed that question in 1905 with his special theory of relativity. The theory began from a striking idea. The laws of physics should be the same for observers moving steadily relative to one another, and the speed of light in a vacuum should be the same for all such observers. This was not how everyday intuition expects the world to work. Normally speeds add and subtract. If someone walks forward on a moving train, their motion combines with the train's motion. But light did not behave like a thrown ball, a strolling passenger, or a crisp packet drifting sadly down the carriage. Its speed in vacuum remained fixed in a deep and surprising way. Special relativity removed the need for the old luminiferous ether. There was no need to imagine Earth pushing through an invisible light-bearing medium. Instead, space and time themselves had to be understood differently. Measurements of length and time were not absolute in the old Newtonian sense. They depended on the motion of the observer. Moving clocks could tick more slowly when compared with clocks at rest. Lengths could contract along the direction of motion. Events that seemed simultaneous to one observer might not be simultaneous to another. This did not mean reality became chaotic or unreliable. Quite the opposite. Special relativity revealed a more precise order beneath ordinary experience. Space and time were not independent containers, sitting separately and calmly in the background. They were linked. The vacuum was no longer simply the empty gap in which light travelled. It was part of a universe where measurements of space and measurements of time belonged together. In 1908, the mathematician Hermann Minkowski gave this new picture a clearer shape. He introduced the idea of spacetime, a single four-dimensional structure combining the 3 dimensions of space with 1 dimension of time. Minkowski's spacetime did not mean that time was just another direction exactly like left or right. Time still had its own character, but it did mean that space and time were woven together more deeply than classical physics had imagined. This was a quiet revolution in the idea of emptiness. Empty space was no longer merely a stretch of nothing between objects. It was part of space-time, and space-time had a structure that could be described mathematically. A vacuum could still be empty of ordinary matter, but it was not empty of relationships between space, time, motion, and light. Then Einstein went further. In 1915, he presented the general theory of relativity. This theory changed the meaning of gravity. In Newton's picture, gravity was a force acting between masses across space. The sun pulled on Earth, Earth pulled on the moon, and every mass attracted every other mass. It worked astonishingly well, but it still carried the mystery of action at a distance. How did gravity cross the emptiness between worlds? General relativity gave a new answer. Gravity was not simply a force travelling through empty space. It was connected to the curvature of space-time itself. Mass and energy affect the geometry of space-time, and that curved geometry guides the motion of matter and light. Earth does not orbit the Sun because it is being tugged through a passive emptiness in quite the old way. It follows a path shaped by the curved space-time around the Sun. A common image is a heavy ball placed on a stretched sheet, with smaller balls rolling around it. The picture is imperfect, because real space-time is not a rubber sheet sitting inside some higher room. But it gives a gentle hint. Matter and energy change the shape of space-time, and motion responds to that shape. In this view, the empty region around the Sun is not simply blank. It has geometry. It has curvature. It tells planets how to move, not with words, thankfully, because the solar system would become very noisy, but through the structure of space-time itself. Light is affected too. General relativity predicts that light passing near a massive object will bend because it follows paths through curved space-time. This was one of the theory's great early tests. During the solar eclipse of 1919, observations led by Arthur Eddington measured the apparent positions of stars whose light passed close to the Sun. With the Sun's glare blocked by the Moon, those stars could be seen near the darkened solar edge. Their positions appeared shifted, consistent with Einstein's prediction that the Sun's gravity would bend starlight. The eclipse results made Einstein famous far beyond the scientific world, though the details of the measurements were more delicate than newspaper headlines suggested. Still, the moment mattered. It showed that gravity could shape the path of light, and that the space around a massive object was not an empty nothing in the old passive sense. Even where there was no air, no visible material bridge, and no ordinary substance filling the gap, the geometry of space-time had measurable effects. This is the crucial point for the science of nothingness. General relativity does not say that empty space is matter. It does not turn a vacuum into air, dust, fluid, or invisible jelly. But it does make space dynamic. Space-time can curve, it can expand, it can respond to mass and energy, it can shape the paths of planets, stars and beams of light. It is not simply a blank container where physics happens. In relativity, space-time becomes part of physics. That changed the meaning of emptiness. The empty stage of Newton's universe was no longer merely a stage. It could bend under the presence of energy. It could carry structure even where ordinary matter was absent. Nothingness, once again, had become less simple. The vacuum was still quiet. But now it had shape. Empty space sounds as if it should be shapeless. If there are no stars in a region, no planets, no gas clouds, no dust, no glowing nebulae, and no passing comet making a brief dramatic appearance, then it feels natural to imagine that nothing much is going on. Just a quiet blankness, waiting politely between the interesting parts of the universe. But general relativity does not allow empty space to be quite that simple. In Einstein's theory, space and time are woven together into space-time, and space-time can have geometry. It can be flat, curved, stretched, expanding, disturbed, or shaped by the presence of mass and energy. A region can be empty of ordinary matter and still possess structure. It can still have paths that light follows, distances that are measured, and curvature that affects motion. The emptiness may contain no dust, no air, and no visible object, yet it is still part of the physical universe. This is one of the quiet surprises of general relativity. The absence of matter does not always mean the absence of gravitational structure. A vacuum, in this context, means a region where ordinary matter and radiation may be absent or negligible. It does not mean that space-time has vanished. It does not mean that geometry has been switched off. It means that the stage has no obvious actors standing on it, while the stage itself may still be curved. Einstein's field equations describe the relationship between energy, momentum, and the curvature of space-time. In voiceover-friendly terms, they say that the contents of the universe affect the shape of space-time, and the shape of space-time affects how matter and light move. The equations are often summarized by the idea that matter tells space-time how to curve, and curved space-time tells matter how to move. It is not a perfect sentence for every technical detail, but it catches the main thought with unusual elegance. The important point is that general relativity treats gravity as geometry, not merely as an invisible pull crossing an empty gap. Near a massive object, space-time is curved. A planet, a star, or a black hole changes the geometry around it. Objects moving nearby follow paths shaped by that geometry. Light does the same. It may seem as if a beam of light is being pulled sideways, but in relativity, the deeper idea is that light is travelling through curved space-time. This means that even the empty region outside a star can be physically meaningful. It may contain almost no matter, but it can still be curved because of the mass of the star. The space outside the sun is not full in the ordinary sense, but it is not geometrically blank. Earth moves through that curved space-time, tracing an orbit that looks, from a classical point of view, like the result of gravitational attraction. In 1916, Carl Schwarzschild found an exact solution to Einstein's field equations. The Schwarzschild solution describes the space-time outside a spherical, non-rotating mass. At first, this may sound like a narrow mathematical case, the sort of thing that keeps chalkboards awake at night. But it became enormously important. It describes the gravitational field around objects such as stars, and it also led to the modern understanding of non-rotating black holes. The striking part is that the Schwarzschild solution describes a vacuum region outside the mass. The matter itself may be concentrated inside the star, or, in the case of a black hole, hidden behind an event horizon. Yet the surrounding empty space-time is not featureless. It has a particular geometry. It determines how clocks tick at different distances, how light bends, and how objects fall. The emptiness outside the object carries the shape of gravity. So a vacuum solution in general relativity does not mean nothing happens. It means the equations are being applied to a region without ordinary matter in that region. Space-time can still have curvature there. A spacecraft, a planet, or a light beam passing through could still be affected. The vacuum has no air to breathe, no dust to sweep, and no furniture to rearrange, which is inconsiderate if someone was hoping to redecorate the cosmos, but it can still guide motion with extraordinary precision. The idea becomes even more vivid with gravitational waves. General relativity predicts that accelerating massive objects can create ripples in space-time itself. These ripples travel outward, carrying energy across vast distances, even through regions with little or no matter. They are not sound waves travelling through air, and they are not water waves crossing a pond. They are changes in the geometry of space-time. For a century, gravitational waves remained an extraordinary prediction. Then, in 2015, the Laser Interferometer Gravitational Wave Observatory made the first direct detection of them. The signal came from two black holes merging more than 1 billion light-years away. As they spiraled together, they disturbed space-time, and that disturbance spread across the universe. By the time it reached Earth, the effect was incredibly tiny, changing the lengths measured by the detectors by less than the width of a proton. Yet, it was enough. That detection showed that space-time is not merely a silent background. It can move, it can ripple, it can carry information from violent cosmic events across regions that look almost perfectly empty. The vacuum between galaxies did not block the wave. It was the very structure through which the wave travelled. This brings the idea of nothingness into a new form. Empty space in relativity can have shape, it can have curvature, it can respond to mass and energy, it can transmit gravitational waves, it can bend light, guide planets, slow clocks, and preserve the mathematical memory of objects nearby. So emptiness is not necessarily stillness. It is not necessarily simplicity. A region may contain no stars, no gas, and no visible matter, yet still belong to a curved and dynamic space-time. In the universe described by general relativity, nothing can be quiet, but it is rarely blank. Relativity changed the meaning of empty space by giving it shape. Space and time became space-time, and space-time could curve, stretch, ripple, and guide the motion of planets and light. But just as physics was learning that emptiness could have geometry on the grand scale of stars and galaxies, another revolution was beginning at the smaller scales. It would make nothingness stranger still. The trouble began with heat and light. At the end of the 19th century, physicists were trying to understand how hot objects glow. A warm coal glows red, a hotter flame shines brighter. A piece of metal placed in a furnace can pass from dull red to orange to white. Classical physics could describe many things beautifully, but it struggled with the precise pattern of radiation from hot objects. The calculations led to impossible results, as if nature should pour out unlimited energy at short wavelengths. The universe, thankfully, does not behave like a broken oven. In 1900, Max Planck proposed a solution. He suggested that energy was not always exchanged in a perfectly smooth flow. At microscopic scales, it could be absorbed or emitted in discrete amounts, later called quanta. This was the quantum hypothesis. Planck himself did not set out to overturn all of physics, while presumably just trying to get a radiation curve to behave. But the idea was powerful. It hinted that the small-scale world was not continuous in the way ordinary intuition expected. A few years later, Albert Einstein used the quantum idea to explain the photoelectric effect, where light striking a metal surface can release electrons. This suggested that light, long understood as a wave, could also behave as if it came in particle-like packets. The universe had begun one of its favourite habits, refusing to fit neatly into a single mental box. Then came the atom. By the early 20th century, scientists knew that atoms were not indivisible lumps in the ancient Greek sense. Experiments had revealed electrons, and Ernest Rutherford's work showed that atoms contained a tiny central nucleus. But this created a problem. If electrons simply orbited the nucleus like little planets around a tiny sun, classical physics said they should radiate energy, spiral inward, and collapse. Atoms should not be stable. Matter itself should be having a very bad day. In 1913, Niels Bohr proposed a new atomic model. He suggested that electrons could occupy only certain allowed orbits around the nucleus, with specific energies. They could jump between these allowed states by absorbing or emitting definite amounts of energy. Bohr's model was not the final description of the atom, but it was an important step. It helped explain the spectral lines of hydrogen, the precise colours of light emitted or absorbed by hydrogen atoms. Atoms were not tiny solar systems, they followed quantum rules. By the 1920s, the quantum picture deepened dramatically. Werner Heisenberg developed matrix mechanics. Erwin Schrödinger developed wave mechanics. These approaches looked different at first, but they turned out to describe the same underlying theory. Particles could no longer be understood simply as tiny beads following definite paths. Their behavior had to be described using probabilities, wave-like patterns, and mathematical states that did not resemble everyday objects. This is where the word uncertainty enters, and it is often misunderstood. The Heisenberg uncertainty principle is not just a statement that measuring tiny things is difficult because instruments are clumsy. It is not simply that electrons are shy, or that nature has placed a tiny "do not disturb" sign on the atom. The uncertainty principle is built into the structure of quantum theory. Certain pairs of properties, such as position and momentum, cannot both have perfectly definite values at the same time. The point is subtle but essential. In ordinary life, a moving object seems to have a location and a speed, whether anyone measures them or not. A rolling ball is somewhere, going somewhere. But at quantum scales, nature does not always assign properties in that familiar way. The more precisely one tries to define certain features, the less precisely another related feature can be defined. This is not a failure of attention. It is part of how the small-scale world works. That changes the meaning of emptiness. If a vacuum is imagined as perfectly empty and perfectly still, quantum theory makes that picture difficult. The smallest scales do not allow every quantity to be fixed with unlimited precision. A physical system cannot always be stripped down into a silent, motionless condition that behaves like absolute nothing. Even the lowest possible state of a quantum system is not necessarily a state of perfect classical calm. This does not mean that quantum physics says anything can happen for no reason. That is one of the most common misunderstandings. Quantum theory is strange, but it is not chaos wearing a lab coat. It has rules, equations, probabilities, and predictions that have been tested with extraordinary accuracy. It does not allow cats to become planets, teacups to tunnel through walls during a quiet afternoon, or socks to vanish into another dimension just because laundry already feels suspicious. Quantum uncertainty is precise. It is not permission for nonsense. Still, it changes what nothing can mean in physics. At the quantum level, absence is not always a simple blank. A particle may not have a sharply defined path before measurement. An atom may occupy allowed states rather than arbitrary ones. Light may behave in ways that are wave-like and particle-like, depending on how it is observed and described. Energy itself can be exchanged in discrete amounts. The deep fabric of matter is not built from smooth certainty, so the vacuum becomes harder to imagine as a dead, empty container. If the rules governing the smallest scales include uncertainty, discreteness, and wave-like behavior, then emptiness must be described with those rules too. It is no longer enough to remove visible matter and declare the result to be simple nothing. The arrival of quantum physics did not immediately reveal the full modern picture of the vacuum. That would come through quantum field theory, but it opened the door. It showed that matter and energy, at their deepest known levels, do not behave like tiny versions of familiar objects. They obey a quieter, stranger grammar. And once that grammar entered physics, even nothing could no longer sit perfectly still. Quantum physics made matter strange. Quantum field theory made emptiness stranger. In everyday imagination, particles seem like tiny objects moving through space. An electron might be pictured as a little speck. A photon might become a tiny bead of light. Quarks might seem like smaller beads tucked inside larger beads, which starts to make the universe feel like a very serious set of cosmic nesting dolls. But modern particle physics does not really describe particles that way. In quantum field theory, particles are understood as excitations of fields. A field is something that has a value throughout space. The simplest familiar example is the electromagnetic field. It is connected with electricity, magnetism, light, radio waves, and all the other forms of electromagnetic radiation. But quantum field theory goes further. It says that the electron has its own field, called the electron field. Quarks have quark fields. Neutrinos have neutrino fields. The Higgs boson is connected with the Higgs field. The particles detected in experiments are not separate little things floating through a background of nothing. They are disturbances, ripples, or excitations of underlying fields. This is a deep shift in the meaning of empty space. If fields are fundamental and spread throughout space, then empty space is not simply a container waiting for particles to pass through. It is more like the quiet condition of the fields themselves. The particles are what appear when those fields are excited. A photon is an excitation of the electromagnetic field. An electron is an excitation of the electron field. The field is the deeper ingredient. The road toward this view passed through some remarkable work. Paul Dirac played a central role by connecting quantum mechanics with special relativity. In the late 1920s, Dirac developed an equation describing the electron in a way that respected the rules of relativity. His theory led to a startling prediction: the existence of antimatter. The positron, the antimatter partner of the electron, was later discovered by Carl Anderson in 1932. This was one of those moments when mathematics seemed to quietly point towards something nature had been hiding in plain sight. Dirac's work showed that quantum theory and relativity could not be kept in separate boxes forever. Very small things can move very fast, and a deeper theory had to respect both the quantum world and Einstein's spacetime. Quantum field theory grew from that need. It became the language for describing particles, antiparticles, creation, annihilation, and the interactions between matter and forces. In this picture, every field has a lowest energy state. This is called its vacuum state. But the vacuum state is not absolute nothingness. It is not the absence of the field. It is the field in its quietest possible condition. That distinction is crucial. A calm ocean is still an ocean. A silent violin string is still a string. A field in its lowest energy state is still a field. It may not contain ordinary particles that a detector would register as passing through, but it is not the complete absence of physical reality. This is why the word vacuum becomes more subtle in modern physics. In older thinking, a vacuum meant a region where matter had been removed. In quantum field theory, the vacuum is the lowest energy arrangement of all the fields. It is not blank. It is structured by the rules of the theory. It has properties, and under the right conditions those properties can matter. The standard model of particle physics is the main framework used to describe the known fundamental particles and 3 of the 4 fundamental interactions: electromagnetism, the strong nuclear interaction, and the weak nuclear interaction. Gravity is not included in the standard model in the same successful quantum way, which remains one of the great unfinished tasks in physics. But for the particles and forces it does describe, the standard model has been tested with extraordinary precision. Within the standard model, fields are not optional decoration, they are central. The electron field, quark fields, electromagnetic field, gluon fields, weak interaction fields, and Higgs field are all part of the structure. What appears to be a particle is a local excitation of one of these fields. Empty space, then, is not empty, because the fields have vanished. Empty space is what remains when those fields are in their lowest available state. The Higgs field makes this especially clear. Unlike many fields that have a lowest energy state with a value that can be thought of as 0, the Higgs field has a non-zero value throughout space. This does not mean space is filled with a thick substance or cosmic syrup. It means that, according to the standard model, the Higgs field has a background presence everywhere. Elementary particles such as electrons and quarks interact with this field, and that interaction is part of why they have mass. The European Organisation for Nuclear Research, known as CERN, tested this part of the Standard Model using the Large Hadron Collider. In 2012, experiments at the Large Hadron Collider announced the discovery of the Higgs boson, the particle associated with excitations of the Higgs field. This was not just the discovery of one more particle to add to a list, it was evidence for a field that helps explain why some elementary particles have mass at all. And that brings the science of nothingness to a very strange place. The vacuum is not the absence of all fields. It is the lowest energy state of fields that extend throughout space. In the case of the Higgs field, even that lowest state includes a non-zero background value. So the modern vacuum is not a perfect blank. It is not ordinary matter, and it is not philosophical nothingness. It is the quietest known state of a world made from fields. Empty space in this view is not where physics stops. It is where the deepest fields are still there, resting. If quantum fields are present even in empty space, then the vacuum is not the absence of everything. It is the lowest energy state those fields can have. That already makes nothingness less blank than it first appeared. But quantum theory adds one more quiet complication. Even the lowest energy state of a field is not perfectly still. This is where vacuum fluctuations enter the story. A vacuum fluctuation is a temporary variation in the lowest energy state of a quantum field. It is not quite the cartoon version often imagined, where tiny particles pop out of nowhere, wave cheerfully at the universe, and then disappear before anyone can ask them to explain themselves. That picture can be useful as a loose metaphor, but it is also misleading if taken too literally. Vacuum fluctuations are not ordinary particles flickering in and out of existence like fireflies in a dark jar. They are features of quantum fields and the mathematical rules that describe them. The reason they appear is tied to the structure of quantum theory itself. In classical physics, it seems reasonable to imagine a field becoming completely quiet. Take away all disturbances, remove all motion, drain away all energy, and perhaps the field could sit in perfect calm. But quantum theory does not usually allow that kind of total stillness. The Heisenberg uncertainty principle tells us that certain pairs of physical properties cannot both be defined with unlimited precision at the same time. This is not simply a problem with measurement. It is not caused by clumsy equipment or a scientist nudging the universe too hard with a clipboard. It is built into the theory. For a quantum field, this means the lowest energy state still has a kind of unavoidable restlessness. Not restlessness in the everyday sense of something fidgeting across space, but a deeper mathematical uncertainty. The field cannot be pinned into a perfectly motionless condition, with every property exactly fixed. There is always some structure left in the quiet. That is an important idea to handle carefully. Vacuum fluctuations do not mean that anything can happen. They do not mean that the vacuum is magical, chaotic, or secretly full of tiny, fully formed objects. Quantum physics is strange, but it is also highly disciplined. It makes predictions with extraordinary precision. Its weirdness is not looseness. It is rule-bound weirdness, which is probably the most intimidating kind. The language of virtual particles often appears in this discussion. Virtual particles are useful mathematical features and calculations in quantum field theory. They help physicists describe how particles interact, especially in processes involving forces. But virtual particles are not the same as ordinary particles that can be directly observed flying through a detector. They are not little temporary marbles darting through empty space with tiny watches, set to vanish in time. They are part of the calculation, not simple objects caught on an invisible camera. Richard Feynman helped make these calculations more visual with Feynman diagrams. These diagrams show particle interactions in a clear and elegant way, with lines representing particles, interactions, and possible paths through a calculation. They're among the most famous tools in modern physics. They can make a complicated quantum process look almost like a neat little sketch, which is both helpful and slightly deceptive. The deception comes if the diagram is mistaken for a literal picture of what is happening. Feynman diagrams are not photographs of the quantum world. They are not surveillance footage from inside the vacuum. They are mathematical tools that organize terms in a calculation. They help physicists compute probabilities for interactions between particles, especially in quantum electrodynamics, the theory describing how light and charged particles interact. Quantum electrodynamics is one of the great triumphs of 20th century physics. Richard Feynman, Julian Schwinger, Shinichiro Tomonaga, and Freeman Dyson all played major roles in developing and clarifying it. The theory explains the interaction between electrons, photons, and the electromagnetic field with astonishing accuracy. In some cases, its predictions match experiments to more decimal places than almost any other theory in science. That level of agreement is difficult to wave away as poetic exaggeration. The vacuum may sound mysterious, but the mathematics describing it has met reality with remarkable precision. One important feature of quantum electrodynamics is that the vacuum affects the behavior of charged particles and light. The vacuum is not treated as a dead backdrop. It contributes to the calculations that describe real measurements. The lowest energy state of the electromagnetic field has structure. When physicists account for that structure properly, predictions become more accurate. This is why vacuum fluctuations matter in the science of nothingness. They show that the quantum vacuum is not a plain, empty container. It is not empty in the same way an unused box is empty. It is a lawful quantum state. It has no ordinary particles waiting around in the simple sense, but it also is not a silent philosophical void. It has fields. It has uncertainty. It has mathematical texture. And this texture is not imaginary decoration. It appears in the deep explanations of measurable physical effects. The vacuum can influence atomic energy levels. It can contribute to forces under carefully prepared conditions. It can shape the way interactions are calculated. The emptiness of quantum field theory is not an absence of physics, but one of the places where physics becomes most precise. So the idea of nothing has shifted again. The ancient void was a space for atoms to move through. The classical vacuum was a region with little or no matter. The relativistic vacuum could have space-time geometry. Now the quantum vacuum becomes the quietest possible state of fields that still cannot be perfectly still. It is empty of ordinary particles, perhaps. But it is not empty of possibility, structure, or law. The quantum vacuum is difficult to picture because it does not behave like ordinary emptiness. It is not a box with all the objects removed. It is the lowest energy state of fields that still have structure. For a long time, that idea could sound almost too abstract, like a strange mathematical whisper from the deep end of physics. Then came an effect that suggested the vacuum could do something surprisingly concrete. It could push, or more precisely, it could help create a tiny measurable force between objects placed extremely close together. In 1948, the Dutch physicist Hendrik Casimir predicted what is now called the Casimir effect. The basic idea sounds almost suspiciously simple. Imagine two uncharged metal plates placed very close together in a vacuum. They are not connected by a spring. They are not magnets pulling on each other. There is no ordinary air pressure between them in the usual sense, because the experiment is carried out in a vacuum. And yet, quantum theory predicts that under the right conditions, the plates can experience a very small attractive force. At first, that sounds like exactly the sort of thing empty space should not be allowed to do. If there is nothing between the plates, why should anything happen? But by now, nothing has already proved itself to be a slightly unreliable witness. The key idea is that the electromagnetic field has quantum modes. A mode is a possible pattern of vibration or variation in the field. In ordinary life, this is a little like the way a violin string can vibrate only in certain patterns depending on its length and tension. The comparison is not perfect because quantum fields are not tiny violin strings stretched through space, and the universe is not secretly being tuned by a very patient orchestra. But the image helps. Boundaries affect what kinds of patterns are allowed. When two conducting plates are placed extremely close together, they restrict the possible electromagnetic field modes between them. Outside the plates, more modes are available. Inside the narrow gap, only certain modes fit. This difference between the allowed field patterns inside and outside the plates changes the vacuum energy conditions. The result is a tiny net force that can draw the plates toward each other. That is the Casimir effect. It is important to be careful here, because this effect is often described too dramatically. It is not simple proof that ordinary particles are popping into existence from nothing like tiny stage performers appearing through trapdoors. It is not evidence that the vacuum is full of miniature billiard balls briefly cheating non-existence. The more accurate explanation is subtler. The Casimir effect shows that the quantum vacuum, when shaped by boundaries, can have measurable physical consequences. The plates are not being pushed together by ordinary hidden air. They are not being squeezed by some mysterious gas left behind between them. The force arises because the presence of the plates changes the allowed quantum states of the electromagnetic field. In other words, empty space is behaving differently because the conditions around it have changed. The effect is tiny. At everyday distances, it is far too small to notice. Nobody has to worry about two dinner plates sliding together across the table because the quantum vacuum has developed opinions about the cutlery. The Casimir force becomes significant only at extremely small separations, usually on the scale of tiny fractions of the width of a human hair. At those distances, forces that seem irrelevant in ordinary life can begin to matter. This is one reason the Casimir effect is important in small-scale technology and precision physics. When devices become very tiny, surfaces can sit close enough for subtle forces to matter. At human scale, the vacuum seems passive. At microscopic scale, its boundary-dependent behavior becomes harder to ignore. Experiments after Casimir's prediction gradually tested the effect with increasing care. In the 1990s, Stephen Lamoureux carried out an important measurement that found results consistent with the Casimir force. Later experiments refined the methods, improved precision, and explored different geometries and materials. As usual, nature did not present the answer with a neat label saying, "Here is the quantum vacuum doing the thing." Experiments had to account for real-world complications such as surface roughness, electrical effects, temperature, and imperfect materials. Physics, like assembling flat-pack furniture, often includes more corrections than expected. Still, the conceptual importance remained clear. The Casimir effect turned a strange idea about the vacuum into something that could be connected with a measurement. Empty space was not merely a philosophical puzzle or a mathematical convenience. Under carefully prepared conditions, it could be part of a real laboratory force. This does not mean the vacuum is ordinary matter. It does not mean nothingness is secretly full in the same way a room is full of air. It means that the physical vacuum is a quantum state, and quantum states can have properties. They can respond to boundaries. They can affect forces. They can leave traces in experiments. That distinction matters. The Casimir effect should not be used to claim that absolute nothingness creates something from nowhere. Absolute nothingness is not what is being studied. The experiment involves metal plates, a vacuum chamber, electromagnetic fields, quantum theory, and carefully controlled conditions. There is already a physical system in place. What makes it remarkable is that even after ordinary matter is removed from the space between the plates, the vacuum state still matters. So the Casimir effect gives the Science of Nothingness one of its most memorable images. Two plates sit close together in emptiness. No visible bridge connects them. No ordinary substance fills the gap. Yet the quantum vacuum, shaped by those boundaries, contributes to a small attraction. Nothing has not become something in the magical sense. But it has gently tugged on laboratory equipment. The Casimir effect shows that the quantum vacuum can matter between objects, but the vacuum does not only reveal itself in carefully arranged plates placed close together in a laboratory. It also appears in one of the simplest places in all of physics, the hydrogen atom. Hydrogen is the lightest and simplest atom. It has one proton and one electron, which makes it a kind of quiet testing ground for theories of matter. If a theory cannot describe hydrogen well, it is probably not ready to describe anything more complicated without looking slightly embarrassed. Because hydrogen is so simple, its light carries extraordinarily useful information. When hydrogen absorbs or emits energy, it does so in precise amounts, producing spectral lines that can be measured with great care. By the early 20th century, quantum theory had already explained much about hydrogen. Niels Bohr's model had shown why hydrogen emitted light at particular wavelengths, rather than in a continuous smear of colour. Later quantum mechanics, especially through the work of Erwin Schrödinger, gave a deeper and more accurate description. The atom was no longer pictured as a tiny solar system, with an electron orbiting like a planet. Instead, the electron was described by a quantum state, spread out in a pattern of probability around the nucleus. Even so, hydrogen still had secrets. In 1947, Willis Lamb and Robert Rutherford measured a tiny difference between two energy levels in hydrogen that earlier theory had predicted should be the same. This difference became known as the Lamb shift. It was small, extremely small. Not the kind of difference anyone would notice while making tea, misplacing keys, or looking suspiciously at a quiet toaster. But in physics, small does not mean unimportant. Sometimes the smallest discrepancies are the places where nature has left a note saying, "Look more carefully." The Lamb shift mattered because it revealed that the earlier description of the atom was incomplete. It showed that the electron inside hydrogen was not simply moving in a fixed electromagnetic attraction from the proton. The electron was also interacting with the quantum electromagnetic field, including the vacuum state of that field. Empty space around the atom was not a passive background. It was involved in the details. This is where quantum electrodynamics became essential. Quantum electrodynamics describes the interaction between charged particles, such as electrons, and the electromagnetic field, including light. It treats the electromagnetic field as a quantum field with a lowest energy vacuum state. That vacuum is not absolute nothingness. It has structure, and that structure can influence particles. One way to understand the Lamb shift is to imagine that the electron is never sitting in a perfectly quiet electromagnetic environment. The quantum vacuum creates tiny corrections to the electron's behavior. These corrections slightly change the energy levels of the hydrogen atom. The effect is subtle, but it is real enough to measure. The vacuum, in a sense, leaves a fingerprint in the atom's spectrum. This does not mean that the electron is being shoved around by ordinary hidden particles flying out of nowhere. That picture is too crude. A more careful description involves the electron interacting with fluctuations in the electromagnetic field, along with other quantum corrections. These are not visible little objects buzzing around the atom like microscopic flies. They are part of the mathematical and physical structure of quantum field theory. Hans Bethe provided an early theoretical explanation of the Lamb shift in 1947. His calculation was not the final form of quantum electrodynamics, but it was a vital step. It showed that the observed energy difference could be understood by accounting for the interaction between the electron and the electromagnetic field. Bether's work helped point the way toward the fuller development of quantum electrodynamics and the method known as renormalization. Renormalization sounds like something invented to make physics students stare silently out of windows, and to be fair, it sometimes has that effect. But the basic idea can be stated gently. In quantum field theory, some calculations produce infinities if handled too directly. Renormalization is a systematic way of relating the quantities in the theory to measured physical quantities, so that meaningful, finite predictions can be made. It does not simply hide a problem under the carpet. It became a powerful method for extracting accurate predictions from quantum field theory. The success of renormalized quantum electrodynamics was extraordinary. The theory could explain small corrections to atomic energy levels, magnetic properties of particles, and interactions between light and matter with remarkable precision. The Lamb shift became one of the key pieces of evidence that this strange framework was not just mathematical decoration, it described the real world. The important point for the science of nothingness is that the quantum vacuum is not only relevant in empty gaps between metal plates, it is also relevant inside atoms, not inside them in the sense of filling them with ordinary stuff, but in the deeper sense that the vacuum state of the electromagnetic field affects the energy and behavior of charged particles. Hydrogen makes this especially elegant. It is the simplest atom, the first element, and the most abundant ordinary matter in the universe. Vast clouds of hydrogen helped form the first stars. Hydrogen still glows in nebulae, fuels stars through nuclear fusion, and appears throughout astronomy as a basic signature of cosmic matter. And in this simple atom, the quantum vacuum leaves a measurable trace. That is a beautiful reversal. Nothingness, which once seemed like pure absence, becomes visible through precision. It does not shout. It does not announce itself with thunder or dramatic lighting, which is considerate for a relaxing evening. It whispers through a tiny shift in hydrogen's energy levels. The Lamb shift shows that empty space is not merely a stage around matter. At the quantum level, the vacuum participates in the fine details of matter itself. The atom is not isolated from the fields around it. Its structure reflects the deeper field-filled nature of reality. So the vacuum has moved again. It was once a philosophical void, then a space in a glass tube, then a region between planets, then a quantum state between plates. Now it appears in the spectrum of hydrogen. Even the simplest atom carries a trace of the emptiness around it. By this point, empty space has already become much less empty than it first appeared. It can have pressure differences in a vacuum chamber. It can act as the arena for Newtonian motion. It can have geometry in general relativity. It can carry electromagnetic waves. It can ripple as spacetime. And in quantum physics, it can contain fields in their lowest energy state. Particle physics takes that last idea and makes it central. In modern particle physics, the vacuum is not simply a region where particles are absent. It is the lowest energy state of all the fields that make up the known particle world. This is a very important distinction. A room with no people in it is still a room. A field with no particles excited in it is still a field. The vacuum in this sense is not the deletion of everything. It is the quietest available arrangement of the underlying fields of nature. Quantum field theory describes particles as excitations of fields. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. Quarks are excitations of quark fields. The Higgs boson is an excitation of the Higgs field. These fields are not placed into space like objects on a shelf. They are part of the basic fabric of the theory. They exist everywhere, even in regions that contain no detectable particles at all. So when particle physicists talk about the vacuum, they are not usually talking about philosophical nothingness. They are talking about a physical state. It has no ordinary particles present in the simple sense, but it still has fields, laws, and structure. It is more like a perfectly quiet sea than no sea at all. No waves may be visible, but the ocean has not vanished. One of the strangest ideas in this picture is spontaneous symmetry breaking. A symmetry, in physics, is a feature that remains unchanged under some transformation. For example, a perfectly round ball looks the same if it is rotated. Its shape has rotational symmetry. Many physical laws also have symmetries, meaning the laws keep the same form under certain changes. Spontaneous symmetry breaking happens when the underlying laws have a symmetry, but the state chosen by the system does not show that symmetry in the same way. A simple everyday image is a pencil balanced perfectly on its point. In principle, every direction around it is equal, but when the pencil falls, it must fall in one direction. The laws didn't prefer that direction in advance, but the final state does. This is only an analogy, and the quantum field version is more subtle, but it gives the flavour of the idea. In particle physics, spontaneous symmetry breaking helps explain why the vacuum itself can have structure. The lowest energy state of a field may not look as symmetrical as the laws that govern it. The vacuum is not just an empty flat nothing. It can have a particular arrangement, and that arrangement can affect the particles that move through it. This idea is central to the Higgs mechanism. In the 1960s, several physicists developed the theoretical framework that became associated with the Higgs field and the origin of mass for certain elementary particles. Peter Higgs, François Engler, Robert Brute, Gerald Guralnick, Carl Hagen, and Tom Kibble all played important roles in this development. Their work showed how particles connected with the weak nuclear interaction could acquire mass while preserving the deeper consistency of the theory. The Higgs mechanism depends on the Higgs field having a non-zero value even in the vacuum. That is the remarkable part. The lowest energy state of empty space includes the Higgs field sitting at a background value that is not zero. This does not mean space is filled with ordinary matter. It does not mean the vacuum is thick, sticky, or sloshing around like cosmic syrup, as tempting as that image may be after a long day. It means that, according to the standard model of particle physics, the Higgs field has a constant presence throughout space. Elementary particles interact with this field in different ways. Some interact strongly with it and have larger masses. Some interact more weakly and have smaller masses. Photons do not acquire mass from the Higgs field and remain massless. Gluons also remain massless, though the strong nuclear interaction behaves in a much more complicated way. It is important not to say that the Higgs field gives mass to everything. Most of the mass of protons and neutrons, for example, comes from the energy of the strong nuclear interaction that binds quarks and gluons together, not simply from the Higgs field alone. Still, the Higgs field is essential for understanding why fundamental particles such as electrons and quarks have the masses they do. Without it, the structure of atoms, chemistry, stars, and ordinary matter would be profoundly different. The quiet background value of a field in empty space helps make the familiar world possible. That is quite a lot of responsibility for something called a vacuum. The standard model is the framework that brings these ideas together. It describes the known elementary particles and 3 of the 4 fundamental interactions: electromagnetism, the weak nuclear interaction, and the strong nuclear interaction. Gravity remains outside the standard model in the sense that it has not yet been successfully included as a complete quantum theory. Even so, the standard model is one of the most successful scientific theories ever created. Its predictions have been tested in particle accelerators and precision experiments around the world. The European Organisation for Nuclear Research, known as CERN, became central to one of the great confirmations of this picture. At the Large Hadron Collider, particles are accelerated to extremely high energies and smashed together, allowing physicists to study the debris of those collisions. The ATLAS and CMS experiments are two enormous detector collaborations at the Large Hadron Collider. In 2012, they announced the discovery of a new particle consistent with the Higgs boson. This discovery did not mean scientists had photographed the Higgs field itself like a landscape. Instead, they detected the particle associated with excitations of that field. Finding the Higgs boson confirmed a key prediction of the Higgs mechanism and strengthened the evidence that the vacuum has the strange structure described by the Standard Model. For the science of nothingness, this is a turning point. The vacuum is no longer just a place where matter has been removed. It is not only a quantum state with fluctuations. It includes fields whose lowest energy state can shape the properties of particles. The Higgs field, in particular, shows that empty space can contain a non-zero background value without containing ordinary stuff. This is difficult because human intuition keeps wanting emptiness to mean absence. If a box is empty, there is nothing inside. If a room is empty, nobody is there. But the particle physics vacuum is not that kind of emptiness. It is the ground state of a field-filled universe. It can be empty of particles and still full of physical meaning. The more carefully physics studies the vacuum, the more it finds structure where ordinary imagination expects blankness. There may be no dust, no air, no atoms, and no visible glow. Yet the underlying fields remain. Their lowest energy state is not the same as nothing. It is a physical condition with consequences. So empty space continues to change shape in human understanding. It is not simply a void waiting for particles to arrive. It is part of the reason particles have the properties they do. Nothingness, in particle physics, is not the absence of fields. It is what the fields are doing when they are as quiet as they can be. The vacuum has slowly changed from an empty place into something more like a physical state. It can be shaped by fields, influenced by boundaries, and connected to the masses of particles. But there is an even stranger possibility in modern physics. The vacuum might not be a single simple condition. It may have different possible states. One of these is called a false vacuum. A false vacuum is a state that appears stable from the inside, but may not be the deepest possible energy state of a field. It is not false in the sense of being imaginary. It can be a real physical state. The word false means that it may only be locally stable, like a ball resting in a shallow dip on a hillside. The ball is not rolling, so it seems settled. But somewhere lower down the hill there may be a deeper valley. If the ball could somehow get there, it would have less energy. That image is only an analogy, but it gives the basic idea. A field can sit in a state that seems stable, because small disturbances do not easily move it away. Yet there may be another state, lower in energy, that the field has not reached. If the vacuum is the lowest energy state of fields, then a false vacuum is a state that looks like a vacuum locally, but is not the absolute lowest possible state. This sounds dramatic, and it can be made far too dramatic very quickly. So it is worth being calm and precise. The idea of a false vacuum does not mean the universe is definitely unstable. It does not mean something terrible is expected. It does not mean empty space is quietly plotting, which would be rude, especially after behaving so mysteriously already. False vacuum decay is a theoretical possibility in some models of quantum field theory and cosmology. It is an idea physicists study because it follows from the mathematics of fields, energy states, and quantum transitions, not because there is practical evidence that disaster is waiting nearby. The physicist Sidney Coleman played an important role in developing the theory of false vacuum decay. In the 1970s, Coleman studied how a field might tunnel from a false vacuum to a lower energy true vacuum through a quantum process. Later work by Coleman and Frank DeLucia considered this idea in the context of gravity and cosmology. These ideas helped physicists think carefully about how vacuum states might behave in the early universe and how different regions of space could, in principle, be affected by transitions between states. Vacuum decay, in simple terms, would mean a field leaving a higher energy vacuum state and settling into a lower energy one. In some theoretical descriptions, this could begin in a tiny region, forming something like a bubble of the lower energy vacuum. If that bubble expanded, it could change the field state around it. But this is not an everyday process. It is not something that can be triggered by ordinary machines, thunderstorms, awkward conversations, or someone poking the vacuum with a spoon. It belongs to the deep mathematics of quantum fields and cosmology. This idea matters because it gives the vacuum a kind of possible history. The vacuum is not necessarily just the blank background after everything interesting has happened. In some models, fields in the early universe may have occupied different states, and then changed as the universe cooled and expanded. The vacuum could have gone through transitions, rather like water changing phase from vapor to liquid or liquid to ice, though the physics is much deeper and not literally about water freezing in space. These transitions may have helped shape the forces and particles seen today. The Higgs field is often discussed in this context. In the standard model of particle physics, the Higgs field has a non-zero value throughout space, and that background value is connected with the masses of elementary particles such as electrons and quarks. The shape of the Higgs field's energy landscape depends on the properties of particles and interactions in the theory. One particle of special importance is the top quark, the heaviest known elementary particle. Its mass has a significant effect on calculations of vacuum stability. Because the measured masses of the Higgs boson and the top quark sit in an interesting range, physicists have studied whether the Higgs vacuum might be absolutely stable, metastable, or unstable within the standard model. Metastable means stable for an extremely long time, even if not the deepest possible state in a mathematical sense. Current discussions often suggest that the vacuum may be near the boundary between stability and metastability, but this depends on precise measurements and theoretical assumptions. It is not a settled practical warning sign. It is a clue about the deep structure of the theory. The universe has also existed for roughly 13.8 billion years. That fact is not a proof of absolute stability, but it is a strong reminder that whatever the vacuum is doing, it has not prevented stars, galaxies, planets, chemistry, or slightly overcomplicated human questions from appearing. If the Higgs vacuum is metastable, the expected lifetime in many calculations could be enormously longer than the current age of the universe. In ordinary terms, this is not something to lose sleep over, which is convenient for a video designed very much in the opposite direction. Still, the possibility is scientifically fascinating. It shows that empty space may not simply have properties, it may have a state. It may sit in one configuration rather than another. It may be stable for reasons tied to field values, particle masses, and the shape of an energy landscape. This is emptiness, not as absence, but as arrangement. The false vacuum also helps clarify why the word nothingness becomes so slippery in physics. If the vacuum can have a value, an energy, a stability condition, and possible alternatives, then it is not nothing in the philosophical sense. It is a physical condition with structure. It may be quieter than matter, but it is not the same as non-existence. There is a gentle strangeness in that. The deepest emptiness described by modern particle physics may not be a final blank. It may be more like the resting position of fields, and perhaps not even the only possible resting position. What looks like nothing may depend on which vacuum state the universe occupies. So the vacuum is no longer just the space left after particles are removed. It is part of the story of why particles have their properties, how fields behave, and how the universe may have settled into its present form. Even nothingness, it seems, may have a past, and perhaps in the mathematics of fields, more than one possible way to be empty. After the strange delicacy of quantum fields, vacuum states, and tiny shifts inside atoms, it is calming to look upward again. Not because the universe becomes simpler at larger scales, of course. The universe rarely misses an opportunity to remain mysterious. But the emptiness between stars has a different feeling. It is wide, cold, dark, and almost silent. A vastness so thin that ordinary human experience has very little to compare it with. At first glance, outer space seems like the closest thing to nothing that nature offers. Step beyond Earth's atmosphere in imagination, and the air disappears. There are no clouds to breathe through, no birds, no weather, no familiar blue sky. The space between planets looks black because there is so little matter to scatter sunlight toward the eye. It feels like a great emptiness, interrupted only by worlds, moons, asteroids, and the occasional spacecraft moving with the quiet confidence of a very expensive metal insect. But even interplanetary space is not truly empty. The sun constantly releases the solar wind, a stream of charged particles flowing outward through the solar system. There are magnetic fields, dust grains, high-energy cosmic rays, and photons of sunlight crossing enormous distances. Space may be a much better vacuum than anything found in an ordinary room, but it is still a physical environment. It has weather of its own, even if that weather involves charged particles and magnetic storms rather than raincoats and regrettable umbrellas. Beyond the solar system lies interstellar space, the space between stars. It is far emptier than anything on Earth normally feels. In many regions of interstellar space, there may be only about one atom in each cubic centimetre. Sometimes more, sometimes far less, depending on the environment. By comparison, a single cubic centimetre of air at sea level contains an unimaginably larger number of molecules. Earth's atmosphere is crowded. Interstellar space is almost deserted. Almost, but not completely. Interstellar space contains thin gas, mostly hydrogen and helium, along with small amounts of heavier elements. It contains dust grains, tiny solid particles made from carbon compounds, silicates, ice, and other materials formed around dying stars and in cold clouds. It contains magnetic fields that thread through the galaxy. It contains cosmic rays, which are high-energy particles moving through space at astonishing speeds. It contains radiation from stars, glowing gas, and energetic events such as supernova explosions. It may look like darkness, but it is not a clean absence. It is a sparse, ancient medium. This thin material is not just leftover clutter. It is part of the life cycle of galaxies. Stars form inside cold, dense regions of interstellar gas and dust called molecular clouds. When stars age and die, they return material to space through stellar winds, planetary nebulae, and supernovae. That returned material can later become part of new stars, planets, and perhaps eventually living things with a peculiar habit of making documentaries about emptiness. The space between stars is not merely empty distance. It is a reservoir, a memory, and a workshop. Intergalactic space is emptier still. Between galaxies, matter is spread across distances so large that the mind has to move slowly to keep from losing its footing. Yet even there, true nothingness does not appear. Intergalactic space contains extremely thin plasma, photons, neutrinos, and the long reach of gravitational fields. Galaxies tug on one another across millions of light years. Galaxy clusters are embedded in hot, diffuse gas that can shine in X-rays. Vast cosmic filaments connect clusters and superclusters, forming part of the large-scale structure of the universe. Even the great cosmic voids, the immense regions where galaxies are rare, are not absolute nothing. They are underdense, not non-existent. They contain some matter, some radiation, and space-time itself. They are like the quietest rooms in the cosmic house, not a place where the house has vanished. One of the most important traces in cosmic emptiness is the cosmic microwave background. This is ancient radiation left from the early universe, released when the universe had cooled enough for light to travel freely through space. It was discovered in 1965 by Arno Penzias and Robert Wilson, who detected a persistent microwave signal coming from all directions in the sky. At first, it was an odd source of noise. Eventually, it became one of the strongest pieces of evidence for the hot Big Bang model. The cosmic microwave background fills the universe. It is incredibly faint and cold today, with a temperature only a few degrees above absolute zero, but it carries information from when the universe was only about 380,000 years old. That means even the darkness between galaxies is crossed by ancient light. Empty space is full of a fossil glow from the early cosmos, softened by billions of years of expansion. NASA and the European Space Agency have studied this background radiation in extraordinary detail. The Cosmic Background Explorer helped measure its spectrum and faint temperature variations. The Wilkinson microwave anisotropy probe mapped those variations more precisely. The Planck spacecraft gave an even sharper view, revealing tiny differences in temperature across the sky that help scientists understand the age, composition, and early structure of the universe. This is one of the great surprises of cosmic emptiness. The more carefully scientists look into it, the more information it contains. What seems like blank darkness carries traces of the early universe, the formation of galaxies, the spread of matter, and the fields and radiation that fill space. The emptiest regions of the universe are not philosophical nothingness. They are thin, cold, ancient environments. They contain particles, fields, radiation, gravity, and history. They may be quiet beyond imagination, but they are not empty beyond meaning. Even between the stars, nothing is never quite nothing. The emptiest regions of the universe are not truly empty. They contain faint radiation, stray particles, magnetic fields, neutrinos, plasma, gravity, and the stretched afterglow of the early cosmos. But modern cosmology suggests something even stranger. Empty space may not only contain traces of the universe's past, it may also help determine the universe's future. This is where dark energy enters the story. Dark energy is the name given to whatever is causing the expansion of the universe to accelerate. It is not called dark because it is sinister, moody, or sitting in a corner wearing a tiny cosmic cloak. It is called dark because its true nature is unknown. It does not shine, absorb light, or reveal itself as ordinary matter does. Scientists infer its existence from the behavior of the universe on the larger scales. For much of the 20th century, the big question in cosmology was whether cosmic expansion was slowing down. Galaxies are moving away from one another because the universe itself is expanding. Gravity, which attracts matter to matter, might be expected to slow that expansion over time. The universe could keep expanding forever, slow toward a halt, or perhaps even collapse back inward, depending on its contents and geometry. Those were the grand possibilities. A very large cosmic menu, though with rather limited dessert options. Then, in the late 1990s, observations of distant Type 1A supernovae changed the picture. Type 1A supernovae are extremely bright stellar explosions that can be used as distance indicators because their intrinsic brightness can be estimated with useful precision. By comparing how bright they appear with how bright they should be, astronomers can estimate how far away they are. Their light also reveals how much the universe has expanded since that light began its journey. Two research teams played central roles in this discovery. One was led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees. They found that distant supernovae appeared dimmer than expected in a way that suggested the expansion of the universe was not slowing down. It was speeding up. Cosmic expansion was accelerating. This was deeply surprising. The universe was not merely expanding from a hot, dense, early state. Its expansion appeared to be pushed, stretched, or driven by something that became more important as space itself grew larger. The name dark energy became attached to this unknown cause. It was a label for a mystery, not a complete explanation. According to current cosmological measurements, dark energy appears to make up roughly 2/3 of the total energy budget of the universe. Ordinary matter, the kind that forms stars, planets, dust, oceans, bodies, books, and biscuits, makes up only a small fraction. Dark matter makes up more, revealing itself through gravity but not through light. Yet dark energy seems to dominate the larger scale behavior of the cosmos. The quiet emptiness between galaxies may be connected to the largest ingredient in the universe. One possible way to describe dark energy is through Einstein's cosmological constant. Albert Einstein introduced the cosmological constant into his equations in 1917, originally for a different purpose. At the time, the universe was often assumed to be static, neither expanding nor contracting. Einstein added the cosmological constant as a term that could help balance gravity and allow a static universe in his theory of general relativity. Later, after the expansion of the universe became clear through the work of Edwin Hubble and others, the need for a static balance disappeared. But the cosmological constant did not vanish from physics forever. It returned as a possible explanation for cosmic acceleration. In this modern interpretation, the cosmological constant can be thought of as an energy associated with space itself. Unlike matter, which becomes more diluted as the universe expands, this energy density would remain constant in each region of space. As more space appears through expansion, the total amount associated with space grows. That makes it deeply relevant to the science of nothingness. If dark energy is described by a cosmological constant, then empty space is not merely an absence of matter. It has an energy built into its structure. The vacuum itself may have a kind of weight, though not weight in the everyday sense of something sitting heavily on a table. It acts gravitationally through the equations of general relativity, influencing the expansion of space-time. The emptiest regions of the cosmos may be doing some of the most important work. This is not the same as saying scientists fully understand dark energy. They do not. The cosmological constant is the simplest explanation that fits many observations, but simplicity does not mean finality. Dark energy could be something more dynamic, sometimes called quintessence in theoretical models. It could reveal new physics beyond the current standard picture. It could also point to some deeper misunderstanding of gravity on cosmic scales, though general relativity has passed many tests with impressive success. At present, dark energy remains an open question. The deepest difficulty is known as the cosmological constant problem. Quantum field theory suggests that empty space should have vacuum energy. That part sounds promising, because dark energy also seems connected to the energy of empty space. But when physicists try to estimate the vacuum energy using straightforward quantum field ideas, the result appears wildly larger than the tiny value associated with the observed acceleration of the universe. The mismatch is not a small accounting error, like losing a receipt behind the sofa. It is one of the most famous and severe disagreements between theoretical expectation and observation in modern physics. This problem matters because it sits exactly where the science of nothingness becomes most difficult. Quantum field theory says the vacuum has structure and energy. General relativity says energy affects space-time. Cosmology observes that the expansion of space-time is accelerating. Yet putting these ideas together produces a puzzle that is still unresolved. The vacuum seems important, but understanding its energy properly remains one of physics' great unfinished tasks. Scientists are not simply sitting around staring at the word dark and hoping it becomes more cooperative. Major observational projects are studying cosmic acceleration in different ways. The Dark Energy Survey has mapped galaxies and supernovae to investigate the growth of cosmic structure and the history of expansion. The Vera C. Rubin Observatory is designed to survey the sky repeatedly and track billions of astronomical objects, offering powerful data for cosmology. The Euclid mission from the European Space Agency is studying dark energy and dark matter by mapping the geometry of the universe and the distribution of galaxies. The Nancy Grace Roman Space Telescope from the National Aeronautics and Space Administration is also designed to investigate dark energy through wide-field observations, supernovae, and gravitational lensing. Each of these efforts approaches the same quiet mystery from a different angle. How fast has the universe expanded over time? How has cosmic structure grown? Does dark energy behave like a constant property of space, or does it change? Are the measurements consistent with general relativity and the cosmological constant, or is something unexpected waiting in the data? The answers matter because dark energy is tied to the fate of the universe. If cosmic acceleration continues, distant galaxies beyond our local group will drift farther away over immense stretches of time. The universe will become colder, darker, and more dilute. Stars will eventually burn out, galaxies will fade, and the night between things will grow wider. That future belongs to timescales so enormous that ordinary imagination becomes very small and quiet beside them. Yet the thought is strangely elegant. The emptiest parts of the universe may not be passive at all. They may be connected to the expansion of everything. The vacuum, once imagined as simple absence, has become a possible driver of cosmic history. Nothingness, at the largest scale, may have a pressure, an energy, and a role in the fate of galaxies. The silence between worlds is not the end of the story. It may be part of what moves the story onward. The question of nothingness becomes especially delicate when it reaches the beginning of the universe. It is one thing to ask what exists in an empty room, or between stars, or inside the vacuum state of quantum fields. It's another thing to ask what existed before the universe was hot, dense, and expanding. At that point, the question begins to lean over the edge of what physics can describe with confidence. The phrase Big Bang can be misleading if it is imagined as an explosion happening in empty space. That is not what the Big Bang model says. It does not describe matter blasting outward from a central point into a pre-existing cosmic darkness. It describes the universe itself evolving from an earlier state that was much hotter, much denser, and much more compressed than it is today. Space was not merely a container waiting for galaxies to rush into it. Space itself was expanding. This is an important distinction because it changes the meaning of before and outside. In an ordinary explosion, there is a location where the explosion happens, and there is already space around it. A firework bursts in the sky. A star explodes inside a galaxy. But the Big Bang model is not a firework floating in a larger room. It is a description of the observable universe growing, cooling, and changing over cosmic time. The early universe was not small in the sense of being a tiny object sitting somewhere. It was dense, hot, and filled with energy everywhere. The roots of this idea go back to the early 20th century. Georges Lemaitre, a Belgian priest and physicist, proposed that the universe was expanding and had once been in a much denser state. He described an early idea sometimes called the primeval atom, though modern cosmology has moved far beyond that original picture. Edwin Hubble's observations of galaxies helped reveal that distant galaxies are generally receding from us, with farther galaxies tending to recede faster. This became strong evidence that the universe itself is expanding. Once expansion is accepted, a natural question appears. If the universe is expanding now, what happens if the story is followed backward? The distance between galaxies becomes smaller, matter becomes denser, radiation becomes hotter. The universe becomes a blazing, compressed state where atoms cannot yet exist, then a still earlier state where nuclei and particles dominate, and then a region where known physics becomes increasingly difficult to apply. This does not mean scientists can simply rewind all the way to absolute nothing. The Big Bang model is extremely successful at describing the universe from a very early hot, dense phase onward. It explains the expansion of the universe, the abundance of light elements such as hydrogen and helium, and the cosmic microwave background, the ancient radiation left over from when light could first travel freely. But as the clock is turned farther back, closer to the earliest moments, the energies become so extreme that current theories begin to reach their limits. That is where the question of nothingness becomes both tempting and dangerous. It is tempting to ask, what came before the Big Bang? But the word before assumes that time was already there, waiting patiently for events to arrive. In general relativity, time is part of space-time, and space-time itself is involved in the universe's evolution. If time as we know it emerged with the early universe, then asking what happened before time may be like asking what is north of the North Pole. The question feels natural, but the usual coordinates may have stopped working. This does not mean the question is meaningless in every possible theory. Some cosmological models do allow earlier phases before the hot Big Bang state. There are bouncing universe models, cyclic models, and proposals involving quantum gravity. These are serious areas of research, but none has become a confirmed replacement for the standard early universe picture. The honest answer is that physics does not yet know whether there was a before in the ordinary sense. One important idea in modern cosmology is cosmic inflation. Inflation proposes that the very early universe underwent a brief period of extremely rapid expansion. Alan Guth introduced a major version of this idea in the early 1980s, and Andre Linde developed important later models. Other physicists also contributed to the development of inflationary cosmology, which remains a powerful and actively studied framework. Inflation was proposed partly to explain features of the universe that otherwise look puzzling. The observable universe appears remarkably uniform on large scales, even in regions that seem too far apart to have exchanged information in the simplest Big Bang picture. Space also appears very close to geometrically flat on large scales. Inflation can help explain these features by stretching a tiny early region to enormous size, smoothing it out while also preserving tiny quantum variations that later became seeds for galaxies and cosmic structure. In some inflationary models, the rapid expansion is driven by a high-energy vacuum-like state. This is where the vacuum becomes an active character in the story of the universe. A field in an unusual early state could have behaved somewhat like a temporary vacuum energy, causing space-time to expand at an extraordinary rate. The vacuum, in this picture, is not just an empty backdrop after the universe appears. It may be involved in setting the conditions from which the later universe grew. That idea is fascinating, but it should be handled carefully. Inflation is strongly motivated and has support from observations, especially the pattern seen in the cosmic microwave background. Yet the exact mechanism behind inflation is still uncertain, and the specific field responsible, often called the inflaton in theoretical models, has not been directly identified. Inflation is not a completed answer to why there is something rather than nothing. It is a proposed description of a very early physical process. Some ideas in quantum cosmology go even further. Physicists such as James Hartle and Stephen Hawking explored models in which the universe could be described by a quantum state without a conventional beginning in time. Alexander Vilenkin developed proposals involving quantum creation of a universe. These ideas are mathematically ambitious and philosophically intriguing, but they do not show that absolute nothingness, in the strict philosophical sense, simply produced something. Usually they still involve laws, mathematical structures, quantum states, or some framework in which the proposal is defined. That distinction matters. A quantum state is not absolute nothing. A law of physics is not nothing. A mathematical framework is not nothing. Even a no-boundary proposal or tunneling proposal does not necessarily begin from the complete absence of all reality, all rules, all possibility, and all description. Physics can discuss unusual states, early conditions, and the limits of time, but it becomes much less clear when asked to explain why there is any framework at all. So the beginning of the universe does not give a simple answer to nothingness. Instead, it sharpens the mystery. The Big Bang model describes the universe evolving from a hot, dense early state. Inflation may describe a still earlier phase of rapid expansion, driven by a vacuum-like field state. Quantum cosmology explores possible ways to describe the origin of space-time itself. But the philosophical question of why there is something rather than nothing remains larger than any confirmed physical model. At the boundary where time, physics, and origin questions meet, nothingness becomes most difficult to hold. It is no longer just empty space. It may be the absence of space. It is no longer just silence within the universe. It may be the question of why there is a universe capable of silence at all. And there, science becomes both powerful and humble. It can trace the universe back to its hot youth, read ancient light, measure expansion, and model the earliest moments with extraordinary skill. But it has not yet shown that absolute nothing can become something. The beginning remains not a blank answer, but a quiet horizon. A black hole sounds at first like the closest thing nature might offer to nothingness. It is dark. It gives back no ordinary light from within its boundary. It seems like a place where matter disappears from view, where space falls inward, and where the familiar rules of escape no longer apply. The name itself almost invites the imagination to picture a hole cut into reality. But a black hole is not a hole in the simple sense. It is not an empty gap where the universe has been punctured. A black hole is a region where gravity is so strong that once something passes within a boundary called the event horizon, escape to the outside universe is no longer possible. Not even light can climb back out. This does not mean the black hole contains nothing. It means that whatever crosses the event horizon can no longer send ordinary signals back to distant observers. The event horizon is not a solid surface. A person falling through a large black hole's event horizon would not necessarily hit a wall at that boundary, though this is not a recommended travel plan, even by the generous standards of cosmic tourism. The event horizon is a boundary in space-time. It marks the point beyond which all future paths lead inward. Outside it, escape is possible with enough speed and energy. Inside it, the geometry of space-time is arranged so that moving forward in time also means moving deeper inward. Black holes connect to nothingness because they can be surrounded by regions that are almost empty of visible matter. Around some black holes there may be glowing accretion disks, jets and hot gas. Around others, especially quiet black holes, the surrounding space may be dark and sparse. Near the event horizon itself there may be very little ordinary material, yet the region is not simple emptiness. It is dominated by extreme curvature, gravity, and the strange relationship between space-time and information. The first exact black hole-related solution to Einstein's field equations came from Carl Schwarzschild in 1916. Schwarzschild found a solution describing the space-time outside a spherical, non-rotating mass. At the time, the full physical meaning of this solution was not immediately clear. Later, it became central to the modern idea of a non-rotating black hole. It showed that general relativity allowed space-time to become so strongly curved that an event horizon could form. The term black hole came much later. John Wheeler helped popularize it in the 20th century, giving a memorable name to something that had previously been discussed with more technical language. It is a wonderfully direct phrase, although slightly misleading if it makes the object sound like an empty drain in space. A black hole is not empty nothing. It is a region where mass, energy, and space-time geometry have produced an extreme gravitational state. For a long time, black holes seemed black in the most complete possible sense. If nothing could escape from inside the event horizon, then perhaps they were perfect one-way objects. Matter and light could enter, but nothing could return. Then quantum theory made the picture stranger. In 1974, Stephen Hawking showed that black holes should not be completely black after all. When quantum fields are considered in the curved space-time near an event horizon, black holes are predicted to emit what is now called Hawking radiation. This radiation would allow a black hole to slowly lose energy over immense spans of time. For large astrophysical black holes, the effect is incredibly tiny, much colder than the cosmic microwave background for ordinary stellar mass black holes, but conceptually it is enormous. Hawking radiation is often explained with a simple image of particle pairs appearing near the event horizon, with one falling in and the other escaping. That picture can be useful as a loose metaphor, but it should not be taken too literally. The radiation is not simply ordinary particles escaping from inside the black hole. It is a more subtle prediction involving quantum fields in curved space-time and the way different observers define particles. The event horizon changes the structure of the quantum vacuum in a way that allows distant observers to detect radiation. This brings black holes directly into the science of nothingness. The vacuum near a black hole is not the same as the quiet vacuum far away in flat space-time. Curvature, horizons, and quantum fields interact. Empty space near the edge of a black hole becomes one of the most revealing places to ask what the vacuum really is. Jacob Bekenstein also transformed the understanding of black holes by arguing that they should have entropy. Entropy is often described as a measure connected with disorder or the number of possible microscopic arrangements of a system. Bekenstein suggested that black holes must carry entropy related to the area of their event horizons. Hawking's later work showed that black holes also have a temperature. Together, these ideas created black hole thermodynamics, a field where gravity, quantum theory, heat, and information meet. This is deeply strange. Temperature usually belongs to matter, gas in a room, water in a kettle, plasma inside a star. Entropy usually belongs to systems with microscopic states. Yet black holes, which once seemed like dark gravitational endings, appear to have both. They are not just empty pits. They behave like physical objects with thermodynamic properties. They also create the black hole information problem. In quantum theory, information about physical states is expected to be preserved. But if matter falls into a black hole, and the black hole eventually evaporates through Hawking radiation, what happens to the information about what fell in? Is it lost, hidden, transformed, or somehow encoded in the radiation? This remains one of the deepest unresolved questions in theoretical physics. So black holes sit at the edge of emptiness in more than one sense. They can be surrounded by vacuum, defined by extreme space-time curvature and dark to ordinary light. Yet they are not simple nothing. They have mass, they shape orbits, they bend light, they may radiate. They appear to have temperature and entropy. They challenge the meaning of information itself. Near a black hole, empty space becomes active in a profoundly unfamiliar way. The vacuum is curved, quantum fields are affected by horizons, and the boundary between absence and presence becomes difficult to draw. Nothingness, here, is not a blank. It is an edge where gravity, quantum theory, and mystery meet. By now, the vacuum has become a very unusual kind of emptiness. It can have fields, fluctuations, geometry, energy, and a connection to the behavior of black holes. But one of the strangest ideas in modern physics is even more delicate than that. Empty space may not look the same to every observer. That sounds almost unreasonable at first. Surely empty space is empty space. If one person sees nothing there, another person should see nothing there too. A blank patch of reality ought to be a blank patch of reality, no matter who is looking at it. But relativity and quantum field theory are not always kind to the word surely. They have a long history of taking comfortable assumptions and quietly rearranging the furniture while no one is watching. In ordinary life, different observers can disagree about motion. Someone sitting on a train may feel at rest, while someone standing on the platform sees the train moving past. Both descriptions can be valid depending on the frame of reference. Special relativity extended this idea much more deeply, showing that measurements of time and distance also depend on motion. Quantum field theory adds another layer. In some situations, observers may even disagree about what counts as a particle. That is where the Unruh effect appears. The Unruh effect is associated with the physicist William Unruh, who described it in the 1970s. The basic idea is that an observer accelerating through what another observer calls empty space may detect something that resembles thermal radiation. In simple terms, an observer moving at constant speed through the vacuum may say there are no particles present, but an observer accelerating through that same vacuum may describe the situation as if there is a warm bath of particles around them. This does not mean the vacuum becomes warm in the ordinary household sense. It is not as if empty space is secretly a cup of tea, patiently waiting for a biscuit and a quiet sit down. The Unruh effect is a theoretical prediction from quantum field theory in the context of acceleration. The temperatures involved for ordinary accelerations would be unbelievably tiny, far beyond anything a person could feel in daily life. To detect a noticeable Unruh temperature, an observer would need an extreme acceleration, not the sort produced by getting up too quickly from a chair. Still, the idea is profound. It suggests that particles are not always absolute objects that every observer must count in the same way. In quantum field theory, what counts as a particle can depend on how an observer moves. The vacuum for one observer may not be the vacuum for another. Empty space becomes less like a fixed empty container and more like a state whose appearance depends partly on motion and perspective. This connects closely with Hawking radiation from black holes. Hawking radiation also involves quantum fields, horizons, and the way different observers describe particles. Near a black hole, the event horizon creates a boundary beyond which signals cannot return to the outside universe. Quantum fields in that curved space-time do not behave quite like quantum fields in ordinary flat space. The result is that a distant observer can describe the black hole as emitting radiation and having a temperature. The Unruh effect involves acceleration rather than a black hole event horizon, but the two ideas are related in spirit. Both show that the vacuum is not simply an obvious emptiness agreed upon by everyone. Both involve the relationship between observers, horizons, quantum fields, and thermal behavior. A horizon, in this context, is not necessarily a physical wall. It is a boundary in what an observer can access or receive information from. For an accelerating observer, there can be a kind of horizon beyond which signals can never catch up. For a black hole, the event horizon marks the region from which escape is impossible. Temperature usually feels like a property of matter. A kettle is hot, ice is cold, a star is extremely hot. A mug left forgotten on a desk becomes disappointingly lukewarm, which is one of the small tragedies of civilization. Temperature is normally linked to the motion and energy of particles in a material system, so the idea that a vacuum state can appear thermal seems deeply strange. But in modern physics, temperature can also emerge from the way quantum fields are perceived by particular observers. The accelerating observer does not merely disagree about speed or direction. In the Unruh effect, the observer's acceleration changes the way the quantum field state is described. What looks like empty vacuum to one observer can look like a thermal bath to another. This does not mean anything goes. It does not mean that someone can simply decide empty space is warm. The effect is not psychological, philosophical, or a matter of opinion. It is a precise prediction based on the mathematics of quantum field theory. The observer's motion matters, not their mood. A gloomy observer does not get a colder vacuum. A cheerful observer does not get a warmer one, though that would make thermodynamics much more sociable. The strangeness lies in the fact that emptiness is not entirely independent of observation in the simple classical sense. Not observation as conscious attention, but observation as physical frame of reference and state of motion. The vacuum is a state of a field, and the way that state is divided into particles and no particles can depend on the observer's path through spacetime. This is another place where nothing becomes slippery. If one observer says a region contains no particles, and another accelerating observer detects a thermal bath, then emptiness cannot be treated as a simple universal emptiness in every context. The underlying field state is described consistently by the theory, but the particle content is not always something every observer agrees on. The Unruh effect has not been directly observed in the simple, clean way one might wish, because the required accelerations are so extreme, and the predicted temperatures are so tiny for ordinary situations. But it remains an important theoretical result because it connects deep ideas across quantum theory, relativity, thermodynamics, and horizons. It helps reveal why the vacuum is not just a dead background, but a physical state with observer-dependent features. So can nothing have temperature? Not philosophical nothingness. Absolute nothing has no fields, no observers, no motion, no thermometer, and no awkwardly cooling tea. But the physical vacuum of quantum field theory can appear thermal to certain accelerating observers. That is not ordinary warmth. It is something more subtle, a sign that emptiness itself depends on the structure of motion through space-time. Nothing, in modern physics, may not look the same from every path through the universe. After travelling through ancient voids, vacuum chambers, curved space-time, quantum fields, black holes, dark energy, and the strange temperature that an accelerating observer may find in empty space, the word nothing has become much less simple than it first appeared. It no longer behaves like one idea. It behaves like a whole family of ideas, all using the same quiet name. There is the ordinary nothing of daily life, an empty cup, a silent room, a dark hallway, a cupboard tragically lacking biscuits. This kind of nothing is useful, but it is never absolute. The cup contains air, the room contains heat, dust, sound too faint to notice, and the patient tug of gravity. Darkness is not the absence of everything. It is a condition involving light and eyes. Silence is not non-existence. It is the absence of sound strong enough to hear. There is also the physical vacuum. This is the nothing that science can actually study. A physical vacuum may contain very little ordinary matter, but it is still a physical state. It can have pressure, temperature, radiation, boundaries, fields, curvature, and energy. A vacuum chamber is not a piece of non-existence trapped inside glass. It is a carefully prepared region where much of the air has been removed. Space between galaxies is emptier still, but it contains particles, photons, neutrinos, gravitational fields, and the cosmic microwave background. Even the deepest cosmic emptiness is not the same as absolute nothing. Then there is mathematical emptiness. Mathematics can describe an empty set, a structure containing no elements. It can describe zero, absence, limits, and abstract spaces with great precision. But mathematical emptiness is still part of a framework. It belongs to definitions, symbols, logic, and relationships. It is not simply nothing in the philosophical sense. It is an idea inside a mathematical system, and that system is already something in the broadest sense. Philosophical nothingness is much more severe. It means the absence of all things, no matter, no energy, no fields, no space, no time, no laws, no possibilities, no structure, and no observer wondering where everything went. This is difficult even to imagine, because imagination almost always smuggles something in. A black void appears, a blank space appears, a silent darkness appears, but a void still feels like a place. Darkness still feels like a condition. Silence still feels like it lasts for some amount of time. Absolute nothingness would not be a dark room. It would be the absence of the room, the darkness, the time, and the possibility of describing any of it. This is why physics has a complicated relationship with absolute nothing. Physics is powerful because it describes states within a framework. It uses laws, measurements, fields, space-time, particles, energy, and mathematical structure. Even when physics describes a vacuum, it is describing something with properties. Even when it describes the lowest energy state of quantum fields, those fields and laws are still present. The scientific vacuum is not pure non-existence. It is a real condition inside a physical theory. That distinction matters. Popular phrases like something from nothing can sound dramatic, but they often use the word nothing in a very loose way. If the nothing being discussed includes quantum fields, a vacuum state, space-time, physical laws, or a mathematical framework, then it is not absolute nothingness. It may be empty of particles, it may be empty of ordinary matter, it may be unimaginably sparse, cold, and dark. But it is not the complete absence of reality. Philosophers have wrestled with this problem for a very long time. Parmenides argued that non-being could not truly be thought or spoken of, because even speaking of it seems to give it some kind of place in thought. Much later, Martin Heidegger famously asked why there is something rather than nothing, a question that still hovers at the edge of science and philosophy. Modern philosophy of science continues to examine what physics can mean when it talks about nothing, especially in cosmology and quantum theory. The important point is not that physics has failed. The important point is that physics has become more precise. It has shown that many things once called nothing are actually rich physical states. The vacuum can have geometry in general relativity. It can have fields in quantum field theory. It can have fluctuations, boundary effects, energy conditions, and perhaps a role in cosmic expansion. Empty space is not a simple absence. It is a measurable part of the universe. Absolute nothingness remains harder to place. If it has no properties at all, then physics cannot easily test it. If it has laws or possibilities, then it may no longer be absolute nothing. The question sits at the boundary where scientific description begins to fade into philosophy. So the science of nothingness does not end by finding a perfect blank. It ends by sharpening the mystery. Every time science makes emptiness more precise, emptiness becomes less empty. The vacuum is not ordinary matter, but it is not nothing. Space may be dark, cold, and almost bare, but it is still space-time, still threaded with fields, still part of the universe's structure. Nothing in the deepest sense may be less a place to find and more a limit of thought itself. By now, nothing has been examined from almost every direction science can offer. It has appeared as a philosophical puzzle, a laboratory vacuum, a quiet region between stars, a curved geometry in space-time, a quantum field state, a source of tiny measurable effects, and perhaps even a contributor to the expansion of the universe. Each time the idea seems ready to become simple, physics adds one more layer. The first scientific vacuums were made with tubes, mercury, pumps, and sealed vessels. They show that air could be removed from a region, at least partly, and that the space left behind could behave in measurable ways. Evangelista Torricelli's mercury barometer revealed a vacuum-like region above the mercury column and showed that air has weight. Blaise Pascal connected atmospheric pressure with altitude. Otto von Guericke's vacuum pump and Magdeburg hemispheres showed that removing air from a space allowed the surrounding atmosphere to press with astonishing force. These experiments did not create absolute nothingness. They created physical conditions. There were still walls, pressures, materials, vapors, temperatures, and surrounding air. The empty space had boundaries and consequences. It was not non-existence. It was a carefully arranged absence. Then general relativity made emptiness even less blank. Albert Einstein showed that space and time are joined as space-time, and that space-time responds to mass and energy. A region can contain no ordinary matter and still have geometry. It can curve, it can guide the path of light, it can shape the motion of planets, it can carry gravitational waves, as detected by the Laser Interferometer Gravitational Wave Observatory in 2015. So even when matter is removed, the structure of space-time may remain. Quantum field theory changed the picture again. In this framework, particles are not tiny independent objects floating in a dead container. They are excitations of fields: the electron field, electromagnetic field, quark fields, neutrino fields, and Higgs field are part of the basic description of nature. The vacuum is not the absence of these fields, it is their lowest energy state. That distinction is enormous. The absence of particles is not the same as the absence of physical reality. A field can be quiet without disappearing. A vacuum can contain no detectable particles and still be filled with the structure of fields. It can have quantum fluctuations, boundary effects such as the Casimir effect, and subtle influences on atoms such as the Lamb shift. Empty space is not empty in the way a drawer is empty. It is more like a silent instrument, still present even when no note is being played. The Higgs field makes the point especially clear. According to the standard model of particle physics, the Higgs field has a non-zero value throughout space. This background value helps explain why elementary particles such as electrons and quarks have mass. The discovery of the Higgs boson at CERN's Large Hadron Collider in 2012 gave strong support to this part of the theory. A field whose vacuum state is not zero is a powerful reminder that even the lowest energy condition of space is not simple nothingness. At the larger scales, dark energy deepens the mystery. Observations of distant Type 1 supernovae in the late 1990s showed that the expansion of the universe is accelerating. The name dark energy is given to whatever causes that acceleration, though its true nature remains unknown. One possible explanation is Einstein's cosmological constant, which can be thought of as energy associated with space itself. If that description is right, then the emptiest regions of the universe may help shape the fate of the entire cosmos. This does not prove that absolute nothingness is impossible in a philosophical sense. Physics cannot easily make that kind of claim. Absolute nothingness would mean no matter, no energy, no fields, no space-time, no laws, no possibilities, and no framework in which a scientific statement could even be formed. That may be beyond what physics can test. Science works by describing states, relationships, measurements, and laws. The moment there is a law, a field, a geometry, or a measurable effect, there is already something. What physics does show is that it has no ordinary example of true nothing. Every scientific version of nothingness seems to retain some trace of reality. A vacuum chamber keeps its walls and fields. Intergalactic space keeps radiation, particles, gravity, and space-time. The quantum vacuum keeps fields and uncertainty. A black hole keeps mass, curvature, entropy, and unresolved questions about information. Even the early universe, when discussed through inflation or quantum cosmology, is not usually described as absolute non-existence, but as a physical state governed by some structure. That may be the quiet lesson hidden in all these empty places. What seems absent can reveal the rules of nature more clearly than what seems full. A vacuum shows the pressure of air. Empty space-time reveals gravity as geometry. Quantum emptiness reveals fields beneath particles. The darkness between galaxies reveals ancient light, cosmic expansion, and the large-scale shape of the universe. Nothingness, in physics, keeps becoming a kind of negative image of reality. It shows what remains when ordinary matter is removed. It exposes the hidden background that was there all along. The more carefully science studies nothing, the less empty nothing appears to be. Perhaps absolute nothingness belongs more to philosophy than to physics. But physical emptiness, the kind science can actually examine, is one of the richest ideas in the universe. Nothing may be impossible to find because wherever physics can still speak, something is already there. So the question returns, quieter now, but deeper than before. What is nothing? At first it seemed like absence, an empty room, a silent night, a dark space between stars. But each version of emptiness slowly opened into something more complicated. The ancient void became a question about whether motion needed space. The first laboratory vacuums revealed that air has weight, and that removing matter from a region produces measurable effects. Relativity showed that empty space-time can still have shape, curvature, and motion. Quantum field theory showed that the vacuum is not the absence of fields, but their lowest energy state. Then the emptiness became even stranger. Vacuum fluctuations gave the quantum vacuum a restless mathematical structure. The Casimir effect showed that boundaries can make empty space behave in measurable ways. The Lamb shift revealed that the vacuum leaves fingerprints inside the hydrogen atom. The Higgs field showed that even the lowest energy state of space can include a non-zero background value. Dark energy suggested that the emptiest regions of the cosmos may help guide the expansion of everything. And yet none of these are absolute nothingness. Physics does not currently offer a clean example of complete non-existence. It offers vacuums, fields, space-time, radiation, geometry, energy, and laws. It offers places empty of ordinary matter, but not empty of physical reality. That distinction may be one of the most important lessons in the science of nothingness. Empty space is not a blank page after all. It is more like the quiet background on which the universe writes its rules. It may be dark, cold, and nearly bare, but it is not meaningless. It carries structure. It holds possibilities. It reveals the hidden architecture of nature. Science has not answered why there is something rather than nothing, but it has shown that nothing, when examined carefully, may be one of the most revealing somethings of all.